Joo. Okei, missä se on? Joo.
Pyörinyt ja mä oon nyt hetken ajanut, mutta ei voi ajanut, koska mä oon niinku restartilla laittaa ajoa niin, miten alussa on enemmän sillä, että vaan 2D-auto.
Joo. On varmaan jotain
ja 3D-auto. Ajoin niinku tietyn matkan ja
se vissi on
kaikki toimii niinku pitää ja sitten vaikka siellä ei ole tehtyä siellä, niin sitten niin tulee ne tehtyä pailit. Näin, että sain 3D-kohtauksen ja näin niin aina tällä hetkellä kaikki lähtää toimimaan. Mutta jos esimerkiksi laitattu semmoinen just lähtenyt tosi supereisiin. Mä olin Madeiralla, että mä olin asunut. Joo. Mä tein Madeiralta etänä töitä ja sitten se oli tossa oli myös semmoinen hetken ollut päivänä teistä ollut viikon päästä, että sitten päivä alkaa pitenee keveästi, mutta sitten on aika kuukauden ihmettää se meni. Joo, kyllä. Onko sä? Joo, meni kiva. Joo. Niin sitten mä jossakin vaiheessa sain mahdilla sen astrotyömässä pyöreän. Mun tekee mielestä, että meillä on niitä todella tehokkaita. Kylläkin sillä...
Se voi kertoa, jos haluaa.
Niin niillä vaihtelee, niin se tehostuu se niin ajoin teho. No niin mä en muista, mutta se on tosi nopeaa, niin todella nopeata pyöriä, mutta mä en tiedä, oliko se vaan jotenkin yhden kerran onnekas juttu vai mikä, mutta niin kuitenkin. Joo. Nyt jännittää toki, että jos pitää nyt uudelleen asentaa se, koska viime kerrasta alkaa loppava vuosi, niin että miten mä osaan etsiä kaikki jutut, jos tulee jotakin, että näin. Mutta sitten mä en tiedä, oletteko se niin asentanut sellaisia, että yrittänyt ajaa jotakin testiä, kun mä ensin testeissä. Niin oikeastaan on sitten ne itse sisäänrakennut testit, koska siinä on se, mulla oli se, että jos Faceillä niin testi menee muuten läpi, sitten kun se testaa niin restart-failia, niin se ei mene läpi. Sitten kun mä niin teen itse sellaisen, niin ajan vähän, ja sitten mä otan sieltä restart-jutut ja ajan näin. Eli kun mä teen sen kaiken manuaalisesti, niin se toimii. Mutta jotenkin se testi, kun se testi yrittää käyttää restart-failia, niin jotenkin se ei mene läpi. Joo. Kiva, jos joku muu pitää tai sitten voi käyttää Suomessa, sitten saadaan jotain pientä porukkaa siihen ympärille.
Tai eikä loppuu jo.
Okei. Joo. Ai niin kuin komput resursseja, joo. Miten niissä Niin on siinä sun puheen perusteella. Tai käsityksestä kuitenkin niin se Reikki on sen suurin tekijä siinä asuksessa. Joo. Miten se rekonnektio siihen vaikutti siellä asteella? Tai jotenkin se hämeni oli siellä ylhäällä. Ja nyt
et syö mitään ja sitten esität kuitenkin sulla on vierestä postelioita raivona venälässä.
mistä se rekonnektio tosiaan? Okei.
Ja nyt kaikki pitää varmaan tässä
Joo.
mun mielestä ne oli niinku täällä kai varannut tän, mikä tää on tilaisuus tässä talossa. Joka on sellainen päätilaisuus. Varmaan se oli jotain kutsua.
Okei. Joo. Tässä on joku naturepaperi, termin helpottaa aloja. Jotenkin niiden tällaista kausilla. Oliko se soloissa ei ole vain vuoren? Okei. Okei, joo, niin, joo, just näin. Joo. Tätä nyt ollaan tarpeeksi tänään, joo.
Ich weiß nicht, ob er das delegiert hat oder das jetzt deshalb hat es mich interessiert.
Es kann sein, dass das die Ausbildung
Vielleicht
nicht mehr hört.
hat er ein bisschen getan. Vielleicht gab da noch
Ja. Joo. No, mä maailmassa niin kuin nyt
Okay, a short announcement. So in this session, please, so in this session the first talk is cancelled. And we want to keep the schedule. So you will now have 15 more minutes to whatever you want. But I also would like to ask if Alessandro Retino is here or not.
I think he just sent an email saying that he will be coming a bit late and he has installed the USB stick. Yes. He said that he will be arriving a bit late to the session and bring his talk with USB stick.
I will ask. But anyhow, his talk is the last one. So
Yeah.
let's hope he will make it. So we will keep the schedule. So we start 11 o'clock.
And he attached actually it as a PDF here, so I don't know which is better. I have that in my email.
Yeah, can you upload it to the links on the website?
mikä nyt on niin sellaista, niin sen tietämistä silloin. Varmaan joo, mä en muista yhtään. Aha, okei. Joo. Haitko viime vuonna pitää HPV? Sä 2 vuotta sitten hait mitä niin nyt täällä tänään 5 vuotta. Joo. Joo, niin se tuli nyt. Ja täällä oli uudelleen. Joo, se tulee nyt uudelleen. Sisäkin voi pohtia, että jos on juttu siihen pitää jotenkin ja askapiammat sitä periaatteessa mutta sehän on portattu niin peulas, mutta niin vaan niin Nvidia siruilla, mutta sitten lumisosi AMD ja sitten näin. Sitten se olisi ihan hyvä. Osaa Jepis. Mulla oli mä olin joku, joka tekee pelkoista olisi, niin sitten sen rekryt olisi ja näin ja noin. Siinä oli vähän sellainen, että mä olin mielestäni tehnyt osoittanut niin vahvasti, miten mä uskallan, että tää tyyppi tulee tekemään sen kohteen, kun sitten sanotaan. Silti oli jotenkin palautetta. Ei ollut varmaa, että pitäisi osata sanoa, että se on hyvä. Niin aivan. Kun niitä GPU:ta tarvitsee, että se lähdetään niin mä ajattelin, ja niitä perusajoja ei kyllä yksi on tosi hyvin. Jotain pitkissä, jos saisi sitä raskautta sinne.
Presentaatio tehdään 330 gigamaa. Se on 3 tietoa.
Aika vaikea muistaa. Mulla on kyllä iso. Tää on taas, mä en tiedä, että tää on ollut vaikka tällä tavalla. Joo.
Let's go.
missään tommosilla simulaatioissa vaan pystyy toistumaan niin. Huomaan, että kertaa
So I just wanted to see this in my words. I guess I would find these keywords.
Ehkä ne pastaa läpi.
Sitten tuossa on tuolla ollut punaamalla, tässä on täysin pilvistä, mutta on syötetty semmoinen vihreä punainen.
Joo.
Aika.
Tää on tämmöinen
massiivinen korona-aika.
Onko tää niinku hajottava, niin onko tää hajottanut STR?
Jees, kuuletko sinä?
Kuulen, kyllä. Odotetaan vielä vähän.
Yes.
Okay, so I think we start now. And the first person to give the talk today is Kalevi Mursula from University of Oulu, and he will give his talk now remote. And Kalevi, you only have 15 minutes time.
Okay, I try to keep it, although as you hear, or at least some recognize, I'm not completely in shape, and sorry for not being able to attend the meeting in person. Anyways, as a kind of starter for this topic, I would like to give you an appetizer of a major storm which is actually ongoing and started last night. It reached so far minus 200 nanotesla, but more particularly it was a very fast CME and exceptionally fast increase of the ring current, so very steep change in the Earth's magnetic field. So very interesting event again coming up. Now this talk is about the long-term occurrence of such storms over the last 100 years. This is a picture of the solar activity. You know the two main ingredients of solar activity being that the activity varies in 11 years, called the solar cycle, and then there are longer term changes which are called Geisberg cycle. They are about 100 years. And the last Geisberg cycle was, or is being called the modern maximum, and the maximum or the peak of this modern maximum was in 1950s and 60s, in cycle 19. So rather than we know a lot of what happens during the solar cycle. We know that quite well now. But what happens during the Kleisberg cycle, if anything more than just the variation of sunspots happen, we don't really know, because this is rather extended period of time, and not very many parameters exist for this homogeneous enough to be studied. And so magnetic storms are the largest disturbances, obviously, of the near space, and they are mainly due to two main solar wind structures. The two main structures causing magnetic storms are the coronal mass ejections. They are actually events that are due to the new magnetic flux appearing on the solar surface, very closely related to sunspots. And then another, they are, CMEs actually produce the strongest magnetic storms. And then there's the other very common storm, which is the high-speed streams and their related shocks regions. High-speed streams are produced in coronal holes, and coronal holes are actually produced by the decaying magnetic flux on the solar surface of moderate intensity. So they are typically a few hundred Gauss intensities, rather than sunspots are something like 1500, so much stronger. We are talking about different types of magnetic elements on the solar surface. But anyway, we call these regions plages that have this moderate intensity, and they are overabundant with respect to sunspots. So the plages cover a much larger area on the solar surface than the sunspots, and they actually also produce more flux to the much more flux than sunspots. Now, magnetic storms traditionally have been calculated by the measurements of 4 stations on ground, and we have actually a server which does this, and it's called the DCX index server. And the magnetic storms traditionally are classified in 4 different intensity categories: weak, modern, intense, and major. Here I mostly combine the two most intense ones to combine them to call them large. Anyways, so we can reproduce these from the storms from 1932 onwards. And this is the yearly number of storms of different sizes. So uppermost panel is sunspot number. You can see the cycles from 17 onwards. Then weak storms, moderate storms, and the large storms on the lowest panels. And you can actually see that the weak storms occur mainly in the late declining to minimum phase of the solar cycle. This is because of this occurrence of coronal holes. Large coronal holes develop in the declining phase of the solar cycle. And the large storms, they follow very closely sunspot cycle, because they are really due to new flux like sunspots. And so in particularly during these first 3 cycles, the cycle of large storms is very closely similar to the sunspot cycle. And this is the, let's say, the ascending phase of the modern maximum. So the modern maximum was during the cycle 19, and these 3 cycles are kind of a growth phase towards the peak of the modern maximum. Now, if you look at the trends, you can see some interesting differences. So in the ascending phase of the modern maximum, the weak storms do not show any particular trend, but the large storms do increase during this time. Also, in the descending phase of or decay phase of the modern maximum, you can see different trends between the weak storms and the large storms. Now, calculating this difference a little bit more quantitatively, you can correlate the two. In the left-hand panel you see the correlation, or actually the time series of the standardized time series of the intense and or the large and weak storms. Of course, they show a lot of almost complete anti-correlation because of their occurrence, different occurrence of the solar cycle. But if you look at the residual between the intense and weak storms, you can see an interesting behavior which is quadratic. And it indicates that there are more of large storms in 1960s and then less of them in 2000s compared to the weak storms. So what does this mean, or what is it connected with? So earlier work that I have mainly done with collaboration with American colleagues shows that there is actually also a related or similar change between the solar EUV flux and sunspot number. Now this is interesting because solar EUV is produced by the same classes as the weak storms are related. So the EUV flux also changes with respect to sunspots in the same way. And here is the on the right hand side especially you can see this quadratic evolution between the EUV and sunspot number. So there is more of sunspots relative to EUV in 1940s, 50s and 60s, and then reversely in 2000s. So this is an interesting and very similar behavior, and it indicates that there are indeed different trends for plashes and for sunspots. Now this relates to the question of how the magnetic fields on the solar surface actually evolve with magnetic activity. So the strongest magnetic fields, the sunspots, they evolve obviously slightly differently to the weaker magnetic elements. And this actually relates to the magnetic canopy structure. The magnetic fluxes that appear on the surface are, of course, they are rooted down in the convection layer, but when they get up to the solar surface to more rarefied plasma, they expand to such a canopy structure. And this expansion is dependent on the strength, overall strength of the magnetic intensity, and it leads to the fact that in 1960s and 80s, 70s and 80s, on the left two panels, uppermost panels, show a magnetic structure which existed at that time with very long field lines between the two hemispheres, and then the lower ones show magnetic field structure in 90s and 2000s with much shorter field lines. And this leads also to the fact that the corona itself is much shorter, is smaller in volume, and the field lines extend to much shorter above the solar surface. And so this is a really interesting change in the solar magnetic structure. And so coming to conclusions already, so this study has shown that storms of different type or different source actually, they vary differently over the long-term, with long-term solar activity and over this 100 years. So that the larger storms, the CME-related storms, occur more abundantly during the growth and peak of the modern maximum, so with high solar activity, than the weak storms. and again the weak storms that are related to high-speed streams, they are more abundant relative to the CME storms during the decay and minimum of this modern maximum. That means that during weaker overall solar activity. So and indeed this means that the different magnetic field elements on the solar surface evolve differently, and this is very synchronous with the change of the EUV flux as shown earlier. So now doing some forecasting. So we are now on cycle 25, and this cycle is already higher than the previous cycle, which was lowest in 100 years. And it seems that we are on the rising side of the another Gleisberg cycle. So we are eventually heading for higher cycles. But the next cycle in our model will not be yet very high at all. It actually will be weaker than this cycle 25. That's our prediction. But anyway, there will be a much larger activity in the following cycle, in cycle 27, and then what happens is obviously that the more intense storms will be more abundant than the weaker storms, and there will be more of sunspots relative to EUV, etc. So because of this fraction of sunspots and flashes is actually a very crucial factor for the stellar evolution of the sun, especially the solar brightness evolution. This has also an interesting consequence to the solar stellar evolution, and also to the possible long-term change of the solar brightness, so therefore also some possible contribution to solar-related climate change. Okay, then thank you very much.
Thank you, Kalevi, and do we have questions? I could ask what Kalevi is causing this. You mentioned this shrinking of the shrinking of corona. Yes.
Shrinking of the corona. Yes.
Yes.
Just a minute. Yes. The shrinking seems to be related to this different to the fact that the strong magnetic fields like sunspots have, they can maintain very long field lines extending from one hemisphere to another one, and of course the weaker magnetic fields can only extend much shorter. Now, if the sunspot related fields decline relatively more than the weaker fields, like it seems now, that means that the fraction of these long field lines is reduced, and because this longest extension of the closed field lines actually determines the coronal extent. So it is actually it determines the radius of corona, if you want to say that. So this means that during active times, corona is larger, coronal volume is larger, and during these bigger times, corona is really smaller. The change is large. It's more than 50%.
Okay, thank you, Kalevi, and let's thank Kalevi again. And then we would move to the next talk, which is by Andreas Wagner. tracking and analyzing magnetic flux flows in coronal magnetic field simulators.
Yes. Okay. So, yep. Hello everyone. My name is Andreas Wagner. I'm also at the University of Helsinki. And I'll be presenting a little bit about my research that I've been doing during my PhD. It was on extracting, tracking, and analyzing magnetic flux drops coming from especially chronomagnetic field simulations, and in particular from the data-driven magnetic frictional simulations that we're doing in Helsinki, among other things. So what we do there is we cut out a voxel of an active region where there was an eruption that we're interested in studying, and then we simulated the magnetic frictional prescription, and in particular we were studying here the active region with this identifier that produced a nice eruption in late 2015. So then when we have this nice simulation, we have a data cube of magnetic field. Where do we find the relevant magnetic field lines that come from, so that take part in this eruption? And for these, I created a semi-automatic extraction scheme for identifying and tracking these structures in the simulation. And in particular, these structures are called magnetic flux drops, which we will see a little bit later. Then the next thing was to make this whole methodology that I created more available to the community. So I also created a graphical user interface that I'll also be showing like a small snippet of. And lastly, with all of this methodology out of the way, we can finally study what happened in this active region. So yeah, first I'll be talking a little bit about the model itself. So the magnetic frictional prescription basically tells you how the velocity evolves in the solar corona, and in particular the prescription is that it evolves proportional to the Lorentz force, which makes things a little bit more computationally feasible compared to MHD simulations where you would have a full momentum equation to solve. Then our magnetic field evolves based on Faraday's law, and I should also note that we have Ohm's law in place, so there's a little bit of resistivity in there as well. So if you then would run your magnetic frictional simulation and you would just evolve it in time, you would see that, okay, this just relaxes to force-free state. However, if what we do is we keep the simulation driven by real observed data, or derived from real observed data, and with that, actually, you would see that with these evolving boundary conditions, your simulation does not reach force-free state, but instead you would keep adding energy into the simulation domain, and with this you can create quite nice eruptions. So again, now that we have the data cube of magnetic fields, how do we get to the magnetic flux shock, the structure that is erupting? So there's a few proxies that people usually use. However, if you want to do this, especially in a time-dependent simulation where you do not prescribe the flux shock prior, so it just naturally develops. Finding these with some proxies and some automated scheme sounds nice, doesn't work. So we need a little bit of our subjective input, and that's where the mathematical morphology algorithms come in, that I'll show a little bit later. In general, so you combine some proxy with these algorithms to get some hold of the structure in your simulation. The proxy that we're using is the twist parameter, which just counts how many turns field line takes about its own axis. And we calculate this parameter in a slice of our domain. So how can we do that? So if we know the boundary conditions, the magnetic field, then it's very likely that if you choose your slice close to the polarity inversion line of the active region, you're likely that your flux rope passes through this slice. So that's how we can reduce basically a complex 3D vector problem to a 2D scalar problem, which makes things a lot nicer to deal with. And in the end, from these twist maps or whatever proxy you're choosing, you can also use squashing factor maps and stuff like that, theoretically. We then extract and track the flux up to time. So I'm now showcasing a little bit the twist map on the, this is your left side. So the colors indicate how strong the twist is. So so yes, the strength of the color indicates the strength of the twist, and the color itself indicates the polarity. So it can twist either left or right-handed. And intuition would already say that like this reddish block might be our flux or cross-section. However, there's a lot of other stuff connected to it, and sometimes the outlines can be quite a bit fuzzy as well. So we need some routines how to deal with these issues, because just applying a threshold will not get you the outlines super nicely. One thing we use is the mathematical morphological gradient, which is a tunable sharpening routine, where you can already see that like the outlines here get a little bit sharper, and this helps stabilize the threshold, so your extraction itself is not as threshold dependent as it would usually be. And then I'm also showing the core piece, more or less, is using the opening algorithm to manipulate the outlines that you get from thresholding. So if you apply the threshold, you get something like this. Yeah, it gets what you want, but it also gets a lot of other structures as well. And to get a hold of that, here I show like a very simple application of the opening algorithm, where it's just applied to the whole map. And that's the blue outlines in the end that you get. The green outlines on some intermediate step that we're not bothering with at the moment. But you can see that it nicely cuts off this one elongated feature here and a little bit from the bottom here. Of course, this is just a very rough application. In practice, you would do this in a sub-window of the whole image. So not using the full one, but like maybe around here. Yes. And to do that in a nice way for all of the snapshots, this can be a lot of fiddling around with parameters and stuff. I've developed Guitar, which is the GUI for tracking and analyzing flux ropes. I also designed the logo myself. Very nice. Yes, and here you can basically fiddle around with all the parameters from both the extraction and also the tracking itself, which basically uses some overlap metric to identify what was in the previous snapshot your flux rope, to also identify it as the same feature in the next frame. And yeah, this is very handy to have like everything on one screen. You don't have to do any scrolling around, running cells in notebooks or whatnot. And you can immediately see the results and visualize the results of all these input parameters that might take a little bit of time to get used to, get a feeling for which parameters you want to use. So once we have that, we can extract from this animation of the twist map now for the full time-dependent simulation various features, and especially the core piece, the interesting one is the yellow outlines. But you can also extract whatever feature you find and then check with the field lines what they are, which is very handy. And in particular here is now the animation of the whole thing. I can see a nice coherent structure of twisted field lines that is erupting from our domain. You can see also here the time-dependent boundary conditions, so the boundary is evolving. And it seems that the simulation is producing a nice eruption, which is good. And also the fact that we see very coherent structure is also a nice verification that the method really works. And yeah, what I talked about before, that you can do different features. Actually here, we could subdivide the flux into two flux that are actually entangled with each other. So this is a nice snapshot showing this as well. And yeah, once we have these simulations, we need to check against observations. does what we simulate, does that resemble reality or not? And for this case, for example, it looks pretty nice. We see a lot of the features that we see in this compound EV image quite nicely. So with this, we can go further and can analyze what's happening in the active region. Now we've done a lot of studies on this, and this is just one sub-thing that we were doing, but here we were trying to analyze the stability of the whole system and what is the likely cause for the system to become unstable. So if you have your coronal flux ropes, it's likely that one of two instabilities is destabilizing the system. It could be either the kink instability, where the twist parameter itself or the twist of the field lines is a governing parameter for the instability. And it could also be the torus instability, where the decay index is the governing parameter. That this basically tells you how strongly the field above the flux rope is falling off with height. And if it falls off strongly enough, then it's likely for the system to become unstable. And we can see here, so if you look at the black lines, so the red lines are from a different simulation, but for the black lines you can see that the twist, once the flux rope is formed, is stabilizing around the value of about 1 turn, which is a common parameter actually for identifying flux ropes, but not really for instability. And on the other hand, if you look at the evolution of the decay index, you can really see that this is going up quite significantly. So this is, in our case, the likely cause for the eruption. Yeah, so that's basically all that I wanted to show. So just to recap, developed a very successful magnetic flux rope extraction and tracking algorithm that has also been applied not just to this simulation here, but to many others, and also not just to magnetofrictional simulations, but also to two different kinds of MHD simulations already. That has worked really nicely. And yeah, all of these enabled us pretty well to study what happened in this particular active region. That I should note also produced a geoactive solar eruption, so this is not just some active region, this is actually an interesting one too, even though most are, in my opinion. And lastly, I should also note that this extraction scheme that I developed, guitar, is also freely available on GitHub, so everyone can go there and check it out. And also, I'm of course also available for questions and guides, feedback is also welcome. Yeah, that's it. Thank you.
Thank you for the very nice presentation and keeping time also. So questions from the audience? You had very nice simulations, so but you need to have some input parameters in the simulations. So, like I guess I saw velocity and current density and perhaps speed. So, which of them do you consider as the most challenging ones to find the correct parameters?
Well, so the input that we use for the simulation is basically electric fields. So this drives the simulation, and yeah, getting the correct electric field. Which we use or which we try to optimize based on velocity estimates that give us an estimate for the energy injection into the domain. So this is always quite a bit fiddling around with the parameters, because yeah, there's how you construct this electric field is not very straightforward, and there is 3 parameters in this. So basically, it's an optimization procedure. And then you still need to check with what produces, so the magnetic field that is then produced, you still need to check with observations. So sometimes you still need to tweak parameters to actually get the eruption nicely. So yeah, it's a lot of fiddling around the parameters, but yeah, the electric field is the crucial point that you really need to get right for the simulation to work.
Is anyone else doing same kind of simulation for this active region somewhere in the world?
Well, in our group, there's a few people who have also done a lot of work on this active region, particularly also because this simulation is just really nice for this active region. And you can study this. If you have a nice simulation, you can study a lot from very different perspectives. And yeah, but yeah, there have also been some observational studies as well. So on the other side of the Sun-Earth chain. But I don't remember all the details. But I think what was nice about this active region is that indeed they found, I think, like two flux-like structures. So it would be a nice verification actually for what we found, that it's actually indeed two entangled systems of flux rods.
Okay, speed tank again. And then we can go to the keynote talk by, so it's about plasma observatory. And Alessandro Vettino will give us the talk.
So, good morning everybody. So, my name is... So, good morning everybody. My name is Alessandro Vettino from FPP in Paris. I'm a co-lead of the Plasma Observatory mission. So I'll try today to give you a flavor of Plasma Observatory. The presentation, I will not go into the detail, yes, there's a lot of material to condense in 20 minutes, but I like, for people who don't know the mission, to keep the essential points, and of course you can ask me all the time. I thanks a lot the organizer to invite me to this. It is important also because this mission is a quite important part of Nordic community. I mean, Scandinavia, Finland. I learned recently that I should not say that Finland is Scandinavia, so I separate in two, and Nordic Baltic countries. So there's a large contribution, so it's important to talk with you today, and hopefully to get more supported. So what is a Plasma Observatory? Plasma Observatory is one of the three candidates for the next M7 ESA mission. Very shortly to say that we are in the final part where we are preparing the scientific and technical review, which is due from February until the end of May, with the decision of which of the three candidate mission will go in June. And the launch is for 2037, so it's something far in the future, and it's something for the next young generation. So it's nice to see a lot of young people here, because this is a mission, if ever selected, for you. So, briefly, the science team is unveiling plasma energization and energy transport in the Earth's magnetospheric system through multi-scale observation. So here you have, and you recognize already the Finnish participation, very important. The Glaciator team is a major simulation tool for preparing our mission. So this is the Earth's magnetospheric region. Basically is where the solar wind interact with the Earth's magnetosphere, and where the strongest energization and plasma transport occurs. So you are familiar, I think, with the forest shock, the shock, magnetopoles, magnetosheaths, and then the tail current sheet and the transition region, where basically the fast flows break and connect to a low altitude. So the major two questions are how particles energize in plasmas, and how are the processes that dominate energy transport in a couple of different regions. So we are a quite large team, more than 400 scientists from 25 countries, including, again, a number of Nordic ones. So Federica Marcucci from IAPS in Italy is the lead, I am the co-lead. So the motivation, basically, it's easy to understand. I mean, you know that plasma is everywhere in the universe, and we can see distant plasma because they emit radiation, which is produced by energized particles. So of course we need to understand all this locally, but also far away. And another things we know from theory, from simulation, and also from common plasma knowledge, is that this is a lot has to do with the coupling of plasma scales. And examples are many. We can go to, of course, our focus is the Earth's magnetospheric system, but we will try also to understand the fundamental processes to help so to speak, understand the similar process in distant objects, like for example supernova remnant shock in the solar corona, which is the closest environment to us, but also farther away things like, for example, plasma jets. And these are also, all these processes bringing to plasma energization and energy transport are related to fundamental processes which are the most studied in our community: shock reconnection, turbulence instability, plasma jets, field line currents, and so on, and the combination of them. And so that's why we choose the magnetospheric system, because it's very highly complex and dynamic. It's really a massive energy transfer and plasma energization. You input, solar wind, pristine solar wind plasma of tens of eV, you ended up with hundreds of keV through all these processes. So this is a massive particle energization object in a solar system. And that's why we go there. But we go there also because in situ we have high quality multi-point measurements, so we can understand really the basics of fundamental plasma physics. We focus on the fluid ion scale, not to say that the global or the electron scales are not important, but just because if you think about where most of the energy goes and where you energize the plasma, these are when the fluid and the ion scale couple, that's you have a lot of action. And then of course we are interested in studying a number of plasma structures, which are often planar, non-stationary, and so on. So we need really to resolve things in 3D at 2 scales. And that's why we need this new measurement, which we actually are not available. And as you can see, the state of the art, as you many of you know, the first constellation in our magnetospheric system was Cluster, which is ending now as we speak. One by one, the satellites are deorbiting, covering the ion fluid. Then we had a very nice mission still flying, MMS, launched in 2015, covering the smaller scale, electron and ion, but none of them could do the coupling at the same time, yes. And so we need a mission like Plasma Observer to cover simultaneously these 2 scales. And the minimum number of points, if you think about having 3D, 1 tetrahedral, as we learned from them, then the minimum number of points is 7 if you share one corner of your 2 nested tetrahedral. And this comes in a very, so to speak, good programmatic international framework. In fact, already in Cosmic Vision, we understood that we needed more point of measurement from cluster, as you can read in Cosmic Vision. And then we did the exercise for the next ESA program, which is called Voyage 2050, where so to speak, the teams of Plasma Observer, the magnetospheric system and plasma cross-scale coupling are clearly mentioned as possible M-class science teams. And we have a broad international framework with Americans. They have in the last decadal survey the LINX magnetospheric constellation, which target larger scale, so very much complementary to Plasma Observatory. Of course, as we speak, we know that the American situation and NASA, of course, which is a part of the United States, is a bit going up and down. We don't know what will happen, but we hope in the future that things will improve. And of course, collaboration with the Japanese as well. And not to forget the ground observatories, yes, which, for example, for Nordic countries is a key thing. And the goal, the ambition is to have a first-time multi-scale coverage from the very small kinetic scale to the global scale. And we hope to do that by mid-2030. Science question, I mentioned already, I don't go into the detail, but a block of questions address the plasma energization in different processes. And so it's trying to understand how this process occurs everywhere in the universe. And then there is a focus equally important on our planet, on the magnetospheric system itself, trying to understand how energy is transferred. So plasma jets, field line currents, instability, and so on. And so these are the spirit of this mission, how our planet works and how we can understand astrophysical plasma. And this is serving a very large community, if you think about your own research topics. I don't go into the detail of the science example. I just give 2. One of the day side, for example, this is the ion injection and shocks. Yes. So how we produce suprathermal ions at the bow shock, which are later during the diffusive shock acceleration produces light energy particles. And the bow shock is relatively small, but so the large energies cannot be attained fully. But definitely you can study in detail how you can inject to suprathermal energies. And then, if you see the different numerical simulation, you see the complexity of the structures which are behind. One example are the slams, which we discovered cluster, where you can see studied also with MMS, which are non-planar, non-linear, evolving in time structure. So where 4 points of measurement are not sufficient, and MMS could do the detail. You see here that the slam with the energization at the same time. We put the detail of the energization, but not the overall picture. So we really need to have 7-point measurements, at least some basic points to resolve the contact and the basic quantities. And at least in 4 points at the ion scale have higher resolution. Similar important problem, but there are many, is the interaction of the plasma jets, BBF, how you want to call it, with the dipole. So on a larger scale you have fluid structures that you can study, but when you look into the detail, you see, for example, here a simulation of how a head of a jet breaks down and creates smaller scale field line currents. So imagine you can have larger separation to study, the BBF structure, which have the order of 1 or a few RE, but you don't know anything about this physics. You can focus on this physics, you don't know anything about the rest. Again, you need the same approach. 7-point and at a smaller scale, higher resolution. Of course, there is a lot of other additional science, because our orbit, we go through regions which are not driving the mission, but will be even more inclusive in terms of science. Ionosphere, magnetosphere coupling, for example, the oxygen outflow, outer radiation belt, and so on. What are very simply saying our requirement? We need to cross what we call the key science region, which are modeled here. We need to have 7 points to have 2 scales into D. Separation has to cover for a few tens of kilometers to thousands of kilometers, and again, basic measurements everywhere with lower telemetry to give the context and compute 3D quantities, detailed measurement in the inner tetrahedron to give the higher telemetry. And so the mission profile is the following. We have elliptical orbit, 7.2 times 17 RE with 15 inclinations, 7 spacecraft, 2 sharing tetrahedron, covering different separation in 3 years, and covering all the science we want to do. This is a cartoon of the spacecraft. The spacecraft are relatively small spacecraft, octagonal ones. They are carrying identical payload, as you can see here, 2 rigid booms with the fields instrument and particle instrument on the spacecraft. You have 2 ion electron sensors covering the full sky, and jetty particle ion composition. And then you have flux gates, search coil magnetometers, and electric field antennas. Typically, we are in the range of the diameter of a bit more than 1 meter, up to 1.5, 0.8 meter height, 2 meter boom, and to about 20 kilo propellant, communication in S-band. We are a spinning spacecraft, yes, at 4 seconds. And the launcher is, we take advantage of the capability of the Ariane 6.4, which can, through its upper liquid propulsion module, can bring the spacecraft directly in operational orbit. Here I don't go into the detail of the instrument capability. I just remind these are the instruments. So we have an ion electron plasma camera, which is a nice new design, allowing to give a very high time resolution up down to 250 milliseconds of 3D distribution. This is done in my lab in France. Then we have the ion mass composition, giving a spin every half a spin, every 2 seconds, 3D distribution of the main mass. This is done in Italy, in the lab of Federica. Energetic particles in the UK, and then the box for all the particles led by Poland, magnetometer in Austria, search coil magnetometer in our country, electric field instrument coordinated by Poland, and the box of the coordinating all the wave measurement by Sweden. So you can see, yes, a lot of Nordic, and if you look into, I don't have the time to explain, but we have contribution also for Finland, for example, important for the energetic particles. Our scientific organization now, as usual ESA does, we have an ESA supported science study team, which is led by Federica, myself, I'm part of it. We are 8 people. We have a supporting group where we have also people from Finland, for example, Minna is here. And for example, Andris Vaivats from Latvia, again talking about Nordic countries. We have a number of working groups, mostly driven by young scientists. One is in the room, Marco Alu, who is the lead of the numerical simulation, again to stress the importance of Gladiator as a support for our mission. multi-point data analysis methods, plasma astrophysics, because the connection with astrophysical processes is quite important for us, additional science, ground observation, public outreach, every career. And this is really, I'm very happy to see a lot of young people here doing major work in this working group and supporting the preparation of our documentation, namely the so-called yellow book, which is a assessment report which is due next month. And then the summary here, again, sorry for not going to the detail, but I wanted you to get a flavor of what is Plasma Observatory. And these are the key things, yes? Is a mission that, in our opinion, will lead transformative advances in fundamental plasma and magnetospheric physics with important implications for other contexts, fits in the Voyage 2050 themes very nicely. It's the natural heritage from after cluster TEMIS and MMS. It fits in a nice international framework also with international partners, a large scientific community, strong interaction, yes, with international partners, but also our key messages here, yes, these two, especially now in these days we speak, it's important that as a Europe we grow strong. We'll form a next generation of European space plasma scientists and engineers, in our opinion. Pioneer it after what was pioneered actually by Cluster. You remember, Cluster 2020 is the first constellation ever to start ESA, so European countries, to do the magnetospheric system. And we leverage our current in new space and small star technology, so there is also an important technical part from industry, from payload teams with new instrument and new technologies. So having said that, and sorry again for rushing a bit, but thank you very much.
Okay, thank you very much for this introduction of this important mission and questions from the audience.
Could you tell a little bit more detail about small sat technologies here?
Yes. Okay. So there is a number of things I cannot say because we are in a competitive phase, so there's some industrial information I cannot share. But I can tell you in general, in a sense that, for example, okay, first of all, the size of the spacecraft is relatively small. To be honest, when we started, we targeted spacecraft which were smaller, about 50 kilos, and we have at least double, if not more, the scale. Other small-scale technologies, small-scale technologies, for example, is related to our OCS way of orienting the spacecraft. So there is an ITT open by ESA, for example, at the moment. And yeah, I would say, you mean exactly on the spacecraft elements? Yes, I mean like. So there is a lot of sub-elements like avionics, which are considering at the moment. For example, there is a Polish company which is called Cryotech, which is in parallel supporting the study. And they are small relatively small spacecraft companies. Yes. Booms also. Yes, we try to. I mean. Again, I cannot say what the primes are doing now for the design, but the idea is also to have like some lighter booms, for example, yeah, more or less. Also antennas for try because we need to spin, so we need to cover the S band, and that was a bit of an issue, yes, to do it. So I think there's an effort also trying to optimize S band antenna for smaller space. We are not using a Star Trek. This was a bottleneck because first of all we don't need it because we are spinning. We can use some sensors which are nicely miniaturized, but also because Star Trek when you start to spin fast, that technology in fact doesn't really exist for small spacecraft. Yes, so this is a flavor of the things we are considering. I can say a bit more if you want later.
Do we have more questions?
Thank you for a very interesting talk. My question is about particle detectors and the energy range. I saw that they reach like some tens of kiloelectron volts, if I remember correctly. So is there a specific reason why to limit the range of that, or are you not interested in higher energy at all? Or
so if you look at the energy range, that's a good question. So we have a thermal detector which is new design, which is able to go to 25 kV, and actually we are doing additional study. Of course, it depends on the size, yes, which can stretch up to 30, yes. And then the energetic particles are starting at 30 kV, and there is the development in a phase A to go down to 20, so to have some superposition. So in terms of superposition of the two sensors, we cover, we have an overlap. Now, to go to the higher energies, this first of all is an error because it's 600, so sorry. If your question comes from that, it's just the type. So we are at 600, and we have the capability, excuse me, this is just a type. We have the capability and of the energetic particle detector to go to about a meter. Now, above those energies in a magnetosphere, the count rates start to get low and so on, and we have contrast of mass, of telemetry, so we are not targeting that, strictly speaking, science requirement. But for the ions, for the electrons, we are happy with 600. For the ions, we can go at a meter.
okay, thank you.
Excuse me for the time.
Yeah.
So I think we need now to conclude this session, but ideally this will be selected. It has been too long that we have had a European magnetospheric mission, so let's
we try our best.
Yes,
okay.
Best for this report. And thanks for all the speakers in this session, so I will now close it, and there's a possibility to go and listen to the general keynote talks in the other. Thank you.
Joo, mä voin käydä ne kanssa läpi. Näin,
Of course, there's some
Yeah. So, do you have lunch plans? No, I don't.
Because Ravi said that he was going lunch with you.
He did? I didn't know. I didn't know this. Maybe he sent an email. I didn't check
Yeah.
it because I was a bit. We are a bit in a negative time. I don't know where he's from. Have you seen it?
Yeah, I think maybe he's in this, like the,
We can maybe
yeah, try to
catch him and
catch
get
him.
him together. Yes.
Yes, and I once again not managing to convert my SVG with the JavaScript positive to PDF, so just wondering should I just give this guy the SVG and hope it works. I mean, it works in our browsers, but they say presentation upload should be PDF.
Yeah. Well, you can go and talk to them.
Yes, but also the file upload is horrible slow. It's uploading, it says it will take 1 hour 47 minutes to upload for this 20 megabyte presentation. What's
From your laptop?
Yes.
Okay, Wi-Fi congestion?
Doesn't seem to be local in this world.
Strange.
Maybe Dropbox is just bad. Bugs are bad.
Maybe Jan is out of bandwidth quota.
Lunch next?
Yes.
Yeah, but I'll do this first. So it might take 3 minutes or 3 hours.
Commenting that Hungarian foreign minister talking about military application to space feels a bit sketchy.
Finished uploading. It said it uploaded 2% and now it said finished uploading.
Nice.
So I'm not sure if this has now happened or not. I also fixed the file in the meantime because there was something wrong. So I will just try again to upload the same.
I managed to embed an HTML file in my PowerPoint that you could open from the, not from the presenter view, but you could kind of like download it out of the PowerPoint and then open it in the browser.
But why?
Because it had the ParaView web-based viewer running JavaScript. embedded
Can I
in this one.
interest you in Inkscape with embedded JavaScript because that immediately runs I have also once during the presentation that had embedded WebGL.
I don't think this is
because you know it's just
actual. Okay.
Oh,
okay.
That's why. So you can embed this one. Yes, you could compile Radiator with Inscripted and run it in the presentation properly. That would be a fun thing. Although I'm a bit scared what that does to API.
There's a little box to make sure that it's put it in correctly.
I'll just challenge Costas to that. He'll manage it. I'll just rabbit hole him in there. I don't think we know that.
Whole new meaning for in-situ visualization.
It said uploaded something, but I'm not sure if that's true.
Oh, okay.
I got Microsoft Edge HTML.
That should be an SVG, something that or should I try to
Right now, can you send it Microsoft Edge PDF? Then,
I can try to convert it to PDF. So,
yeah,
I mean,
then it'll work with this.
fundamentally, it's a browser-based tool. I can also convert it.
Why not?
Because actually? Downstairs. Upstairs.
It's not a problem, we are not in that
Yeah, for me it said it takes like 76 minutes and then when it's 2% it's done. Oh, okay. So I have no idea what's going on there. So the problem is actually the video in my face.
Alright, but that's not a problem. I will stay here for 3 days on the conference. And then on... And nobody can come to that you would think that you... I'm not sure, but I wouldn't bet that...
Or maybe it is my internet because it's supposed to work. But also my payroll currently does not connect because once a year I need to change my password and I changed it in the payroll config. Connecting.
What time is it? On Friday we'll come at 10 to Kumba campus and then in the afternoon I am more or less free so I can come here 4 or 6. But you must agree with Yes, yes, we will. So will not come on Friday before. Okay, then we are not in a hurry. We were already doing the change of plan for you that we could finish even today or on Thursday, but if you don't have it with you, then we are not in a hurry. No. I only do it Friday, the Thursday afternoon or
What?
Friday morning.
Account locked out, tells me video.
I didn't want to actually stress anyone.
Why am I locked out?
Yes. There was a misunderstanding. I don't know what did I mistake with the date, but I thought it was Friday after this meeting. Well, then
Windows
is not that comfortable at the moment. So okay, we can
Excuse me.
Let's finish one.
Also,
Hacking too hard.
hacking too much time.
We are just discussing the instrument, so we keep in the classroom 40 degrees for a long period. Some elements so much.
So it's not fundamental.
Really, okay.
Why would not the island? This is so weird. Oh, but no, here I have access from here directly. I like computers.
is your name?
Yes, yeah.
Is it this?
Yes. Alright, perfect. So I'll get right over to you with the video replay in your yes, yes. Okay, that's fine. Okay, yeah, also, yeah, back. Yeah, that's also good. No. This okay.
Yeah, no, there's one. Is this supposed to?
Yeah, sure. So can you click on? Yeah.
This cannot play.
Yeah. Still, yeah, still I have it.
Well, can you just quickly see the other ones go?
Yeah, that is good.
Okay. Nothing here.
Yeah, it's not a movie.
And then, yeah. So yes, it's just this one which.
Yeah. I don't know what.
It could also just be because like I started it and then I went back, so I'll just try it.
Okay.
Can I ask you because I'm not familiar with it. What is Laziter?
Okay. So this is just simulation model. So this is simulation model. So
Is it like developed by
yes, yes.
I see.
If that, I mean, if this one is not working yet, I think I will try to modify this path only, and I think we can, I can also upload the new one.
Okay.
The meantime. So because my session has, my presentation states 30, I mean 230, so I still have time.
Yes, yes.
I'll try. Yeah. Why not? Once animation is not playing. Somebody's.
Hello, hello.
like alcohol beverage one. Or no, this one has alcohol.
That is no. None of them has alcohol. You shouldn't.
These ones, so just assuming they're alcohol. Oh, I know.
Yeah.
So those ones are fine.
Okay. This is doctor.
Yep, that one's good. This is good.
Okay. There's a camera in the back of the room. Okay, that's okay. So you have the presentation for the afternoon session. You're going to be here after.
Yes.
Okay.
I have a full.
Oh, this is the one. That is the camera.
Right, I thought you could test other cameras as well.
Well, that camera in the back is not connected here.
Oh.
Yeah. Okay, but so the presentations for the next session are available.
Yes.
Okay. And you have the audio. But we're still using Zoom.
Yes. Zoom is working. Stay stream. I'm sure.
Okay, because technically there should be like the guys from Game Polygame wanted to switch to YouTube, but I guess it's not. Oh, this is here. Yeah, so the YouTube live stream actually works now.
Should we switch to video? About the presentation. Huh? About the presentation part.
Yeah, so this is YouTube. It just has a delay of like a minute.
Nice.
Okay, that's good. Did you not know that we're live streaming on YouTube?
Well, I heard that we were, I didn't know it was also.
Yeah. So the technical guys didn't talk to you, but
They're just like, excuse me?
this is the problem. The community, like, they don't tell anything. So that means we don't need the Zoom session, yeah? On any online presentation for the next session.
Are they? I don't think so.
Well, like some people may present on Zoom, so maybe it's still fine just to keep it on just in case for those people. So.
Okay. So the Zoom stream looks okay.
Should we pull up the YouTube stream for comments?
I don't think there's
I don't think it's 1 minute away.
Yeah.
Also, that microphone doesn't seem.
This one, yeah.
Yeah.
I just take the battery out to charge.
Oh, no, we charged it before and it went green, we put it back in and still didn't turn.
Oops. That's not good.
Oh.
I have 4 batteries, so I can check.
Also, I'm going to do lunch real quick.
Oh yeah, yes, guys, try to get lunch. Then you can.
One of us has to be now.
Well, at the moment, if there's no presentation.
From YouTube one.
Yeah, probably not. So we call past the 15 minutes to catch lunch.
When's the next presentation?
No, we haven't put on for today.
Okay. This one room has all right. Okay. Yeah. Okay. Then you have time. We have not everything. Actually, I'll get some batteries for that one.
I just get the lunch ticket at the desk.
Yes, exactly. Yeah, it came up on the show. Where did we get the coupon? At the reception.
Okay, thank you.
I am doing the annoying task of converting this to PDF, which means opening every slide in the browser, pressing print, waiting for 20 seconds for it to discover that it has no printers, only offering print to PDF, saving that to PDF, and then concatenating those, which works, but is...
I have to say, you are not selling this SVG thing very well to me.
No, it has its drawbacks if you want to do something, or somebody wants PDFs from you.
That's the thing. So, how long do you think it will take?
10 minutes. I suppose I need to somewhere.
So, shall we go?
Do that. Food is good for you. Give you strength. Fight with computers even more. Now I've uploaded to PDF as well. That took a while. I had uploaded only an SVG that rendered it wrong, but now there should be Takka PDF.
Okay, yes. You just upload right now, please. Okay,
There should be a SVG from a couple minutes back.
yeah. Yes.
So we can get for lunch. Yay! Thank you.
how does man do this?
So for PowerPoint slides, I just open it from the file there, and we can test it right now.
So we go to and go to the schedule. So there is this
Yeah, that's the student.
lorry.
So that's the speaker there.
Oh, I
Send
see.
it for middle one.
Is that like mirror the mirror?
I'm the mirror. So,
Ah.
so I uploaded 2 files there. So second one has 2 at the end. So I'm like that one. If possible. It should be like Palmu dash
Yeah.
mirror dash
Yeah.
presentation.
Oh,
Oh, so we,
alright, I'll do that.
it's in that. Did you do this? Or, these are actually the next one. So we have,
One, two.
yeah, this is the one.
Yeah, but the other one.
They are. This is the last one.
Oh. Right.
Yeah.
Okay, let's just have the next one. We're looking for this.
So let me show you how to open this. So as a PDF, this has to be like
Yeah, open that.
acrobats. And on it, control.
Control.
I don't think you have to drag it.
Okay. Who's the next mark?
Yeah, this is there. Files.
Do you have lunch with someone?
I do, so.
Oh,
I don't know anyone who wants this, so. I just volunteered to get the points.
What?
See what?
Oh, this is Footsie Country.
Yeah.
Oh, I see.
So I think that,
I heard apparently, I'm not sure about this, but I heard apparently when secondary you just go up and get it.
okay.
I'm glad to hear that you're about to have. There's many people in my major who aren't, which is expensive. Yeah.
I think it is kind of nice.
It is kind of pricey, but I think like,
Wait, what you said?
I'm studying chemicals.
No, but yeah.
But I'm not doing this for the Footsie Country. Just for the sake of doing it. Yeah, that explains it. So then you're not actually part of ASA. What's your?
Just a random.
Are you interested in space and stuff? Or not?
I think it is interesting, but I don't know if it's something
Interesting to you.
career in the future. Yeah. It is old school.
I mean, of course, this spirit can influence you. It's all about, career influence.
Yeah, but I don't know what else going on. I'm confused about.
This is,
I'm not smart enough for this stuff.
this is pretty advanced. We're bachelor students. So then what does, like, or in your mind, like, what is your ideal job?
It's a job where I can design and manufacture my own things. For example, robotics. They're very, very hands-on.
I thought you were studying data science.
Digital system design.
Is that school of art?
No, it's school of electrical engineering.
So, alright. Is it that electrical design?
Well, the major is mostly electronics and building all sorts of systems from the ground up, and but with a heavy emphasis on design as well, such as like user interface and how doing tons of tests on users are.
You have the hardest job in anything. It's just like making it work, I guess.
Yeah,
Because
make
it's
it work
like,
properly.
yeah, it's so easy to like okay, you can make a machine, but it's like running in console, you know, or like terminal lines. That's just horrible. But then the effort it takes to properly polish that.
Yeah, my first project that I finished was fairly simple. It was like automatic toilet paper dispensing.
And you make that yourself?
Well, I was in a group.
Yeah, but I mean still, like that's pretty.
Yeah, each of us had our role, and my role was to I designed all the parts and using that.
What do you use, Fusion? Fusion's good. I mean chemical, but then I had to design a warehouse. They're using AutoCAD. You store chemical? Not just a warehouse. Because technically, I'm in the English speaking program, which comes under School of Science. Hence, I have to also do that other stuff as well. I'm not in the School of Chem. That's only it's a bit weird. So, how many food sequences are you into the parties and stuff?
Oh. I think I have about 50 points.
Oh my goodness gracious. Okay, this guy's just leaking with points, man. Give me some as well. Because, yeah, I need to. Can you give me my bag? I think. I have done exactly that when I've been to that many parties so far.
That's one of the best parts.
The thing is, I don't drink, so then.
Okay, I understand.
Yeah, you gotta drink to do the parties. How did your food card look so cool?
Yours is other places?
Hell no, ours is it's a green booklet. And it's like the lowest quality paper, like literal toilet paper.
Nice designs and everything.
Yeah, it's sick, man. Hey, you got your captains and stuff? It's actually ours is genuinely a green booklet with the logo. No, it's utility driven, I think. Very utility driven, very efficient, you know.
That's right. So it's like there, campus restaurants.
Well, wait, you need 50, because in mine 30 is enough.
Yeah, here, 30 points. So that's good. But I definitely one, three, 46.
Dude, someone said about E1. Oh my god, what? Oh. Dude, Loki, you have to call that.
I have an A1 at home.
Okay, a mini or a proper?
Proper. A1.
You live here?
Yeah.
That's
I have the AMS as well.
Yeah, that's actually I think, actually, it might be your
I got my A1 with an AMS. It was like 500 or something.
Bro, it's 189 new. It's a 299 new, and he's selling it for 280. We got a hustler in the shop for us.
I wonder how many hours are on it as well. If it's like really low hours, like 50 hours or something, then understandable. But if it has thousands,
But how come you bought the 8? I mean, okay. The thing is, I have a H2C, but it's literally it's in an unenclosed room, so it smells of the entire place. So I have to buy they sell
Closure. No, 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 HTC, it's this one. Oh, okay, okay. I have to, like, they sell smoke purifiers. Are you vegan this week? Well, I kind of have to in the new year. It's mandatory. And this,
I love to.
so I had to, like for the projects, I designed a cat and then 3D printed it home. I also 3D printed stuff like this. I'll show you. Dude, oh my goodness, it's so cheap. You get a $50 discount if you register your account for the first time. So you can literally buy a brand new one for cheaper than you just reselling. Scam for this guy. Print stuff like this. How's the? Ooh, wait, this is FDM. Yeah. Dude, what 0.2 mm? Yeah, smallest possible. Because this, I have never seen this much detail. This is, because like, dude, you could almost say that this is resin. Yeah, it's really, really, it's very fine-tuned settings. I think the layers were 2.06. That's, and I used PLA Meta from some of the. Oh, you don't use the bamboo for this? I have bamboo, but I used this this PLA Meta for detail prints because it has a I think a lower melting point, and it's very very smooth when it goes on, and it kind of like melts together layers. That's why it looks really really clean. You have to really squint to see the layers. Do you have you considered using ABS and then you can like get rid of the layers using acetone reader? Yeah, I've seen it. I don't know. I think this is already good enough. That is extremely impressive. Like, if you hadn't told me, I would see that was resin for sure. You really have to like put it in the light and then look carefully at all the edges. Then you'll see the lines. If you would prime this and then paint it, you cannot tell it's it. That is really good. Yeah, dude, mine, I printed 0.8 so my mind are nice and big. I usually print like really big, like so. Do you know how long this is to print? I can guess. Yeah, guess. Yeah, okay, 0.2 mm nozzle, 0.06 hours. Dude, I almost want to say like 6-7 hours. No, it was 3 hours. No, for 3 hours this is really good because I mean, you can't. I'm assuming like when it's this detailed, you can't move fast unless it's stringy. This is actually with bamboo. That's bamboo. You can compare. Is it PLA? What is it PLA? It's just regular PLA. The basic, nothing special. Just the most basic PLA. Still, like, the layer lines are really hard. I mean, especially at this, like, so. This is proper stuff, and this is your texture PLA. Yeah. Don't play it down. That's all that you should have. You don't think the cold plated ones are worth it? Which one? Like the cold plates, yeah. The thing with smooth ones is you need to use glue, otherwise you don't get that adhesion. And if you're using glue, you have to wash it. I have the smooth plates. I saw some flat plates they don't require glue. It's called like the ice one or something. Oh, that I don't know. I just know the official bamboo plates, which are what do you call it? It's just official. Deep freeze. Do you mod your email? Like software one? Or just not hardware. You know, people put like the little Mike Wazowski or something. Oh, I just put Google eyes on the printer. So every time it's moving, the eyes are moving. And then I just printed some accessories to put all around it. So I printed out a set to put the AMS attached to the top of the A1, so it's all just like a tower, so it saves a lot of space. So I'm assuming you lived here before you joined Alpha for sure. Yeah. So when did you already come over? Or have you solved it? I came here 3 years ago. Where are you from? I'm actually
yes.
Yeah. You just came in?
Did you upload your updated one? I think it's still plays in my computer. So I don't know what's happened. There might be something wrong with this one. I can try again. To upload it? Yeah, I did upload it, but one of the animation is not playing in the computer. Let's see if it's stable.
No, I think you can come here to check.
Yeah.
We can look through real quick on the screen.
Yeah, what's the next one? This one? No, the next one. Next, yeah, I think this one. This one doesn't work. Yeah, it says cannot bring the music. Yeah. Yeah, I think it's not that much for that song. Yeah, the rest of them work. Yeah, the others. You can see this one. Yeah. How are you doing? Your kids?
The kids are growing already 8 and 6 years.
Just like in school.
Yeah. At least for me, though. 18. Did you go all
Last
yeah.
Louisiana?
Yeah, I mean this year. Yeah.
I didn't go.
Yeah, you did.
Yeah.
Yeah. It's San Francisco.
Okay. Then when plan to go this year.
Okay.
I skipped the New Orleans.
Yeah.
You went?
No, I made good yeah, the condition was not that comfortable to go. I cut my position in
Anywhere outside of the general transportation area.
It's let's see
yeah, there's
happens this year. You never know
yeah.
what can but
that guy is the rest of the videos. Okay.
every day something.
I mean, this year is really special. Everything. I mean, every day is something there making some noise.
It might feel like if things go really well, so you have to nobody goes right up.
Yeah.
If that kind of thing doesn't happen, so there's
yeah. I think the good thing is now the NASA got the funding.
they got it now.
Yeah, because I think it's I mean that week, I mean last week that he cut that funding, but now the
Yeah, it has been promising. It's coming back to almost normal, but it's just wondering is it now finalized or
yeah, not yet. Yes.
Okay.
Yeah.
Okay. Congress has to
walk through the image now, and it will take like half a minute or so.
Let's see.
Yeah, it's crazy. I don't know.
Could have been a disaster.
Yes. And let's hope
it
that
has been kind of disaster. Some already many people left. Did not come back.
yeah. Okay, that's going to be asking questions.
Some
Okay.
because of these things, people were back to Florida. Professor
for a long time. But now it's again.
University School of
Yeah, I think that's
That one always was working.
civil servant.
Both work. Oh.
Yeah, but
Can we maybe put the replacement button like her?
lot of new prices that you haven't been all this.
Yeah, no, we should do some.
All possible prices now we have so we will be happy.
Yeah, it shows green.
So we got the football express and then second hand Nobel Prize. Maybe the big committee. Ice hockey.
I think that you calm me down. We lost an umpire right now.
Okay. Yes.
There's someone who's selling a 3D printer for full price. I'm sure all of these, you know, the waste.
Actually, national engineering building, they have the latest what do they call it? No. Yeah, I think they have two. Or it's gonna be super, not just able to use them. You have to clear emergency.
Dude, there's an X one in where we're based at Asa Space. And my god, the poor guy has a mystery that's so bad. It's like the X one is like a novel blog, it's about the last X. I saw that, I thought it was yeah, I think it's more like the students like over here because like it's not your machine, so I'm like careful.
Maybe they just don't check.
I
see the settings that, oh, they didn't change in the program. Nozzle on the printer is this, program, it's another nozzle, and then
you know, the X ones have a problem where like whatever you do, like it crap out, right? Like you can fall back under it, like the regular thing, and then you can get it smooshed. And there was a ton of them. And no one ever checked it. So I saw that and it is. That's why that's the new ones are like really I mean they also laser cut and that's coming around. When there's no light, it's blue, and when
That's good enough.
Suoraan lukuun päästä sun mielestä.
Mä oon ensimmäinen esittäjä, että onks mä nyt vai?
Hyvä. Täysin hyvin, että siinä on just silloin, kun mä lähdin mekanismikursseja näitä se jatko-opiskelijat käytännössä valmistui siinä vaiheessa niin ryhmä on vähän uusi se ja sitten uudestaan näin ja just noiden kanssa säännöllisesti tekemisessä niin oli ikinä mennyt vaikka on kaikkea ikinä näiden kautta sitten on väistettävä Niin on. Vielä olin siellä. Aika hyvä.
Good afternoon. Okay, good afternoon everybody. So this is a session titled Numerical Modeling of Space Plasmas, and we have 5 presentations, 15 minutes each, and first speaker is Miro Paalmus.
Yes.
Floor is yours.
So, hello? Is this good or?
Oh.
Sorry. Hello? Hello? Hello?
It broke. Okay, now.
Oh, yeah. Yes. Okay. Should I go without or like? Oh, because we need it so that people online can also hear. Okay, I'll try.
So.
Okay, let's go without and we'll figure it out.
Actually, you can take it off for now and try to see what's wrong with it.
Okay, so for you here locally, I'm Miro Paalmus. I'm quite fresh PhD student from University of Helsinki in Center of Excellence of Neutron Stars. Title of my talk is Relativistic Plasma Simulations with GPU Accelerated Rungo Code. So we do astrophysical plasmas, and often these plasmas are relativistic, which means that noticeable fractions of the particles in the plasma move at relativistic velocities. These often occur when there is sparse plasmas which interact with high energy density objects, such as like around a neutron star, like neutron stars' magnetic fields. We describe plasmas with like kinetic plasma descriptions. We have this, maybe most of you don't already notice, but we have this distribution function, which is function of time, position, and here we use 3 momentum. And this Vlasov equation describes how it evolves. And it contains three terms. First term is the time derivative of the function. Then we have this term that describes how the distribution evolves in a space, and then we have this last term which contains Lorentz force, and it describes how the distribution evolves in the velocity space. And if we want then to simulate this, simulate plasma using, we have many different kind of options for doing these simulations. And one of them is to solve Vlasov equation directly, but this is computationally expensive and memory intensive, but this can be done, and you will hear about this later in the next talks from the glaciator people. Then you can also do magnetohydrodynamics, but it uses approximations for the velocity distribution, so it doesn't apply for cases which interest us. Then you have this particle in cell or peak method. It's this Monte Carlo type sampling of the Vlasov equation using particles. There is no approximations. It's relatively simple to implement, and it's computationally cheaper than solving the Vlasov equation directly. So that's what we do. We have this Rungo code. It's a toolkit for simulating astrophysical plasmas using particle in cell method. Originally, it targeted CPUs, but it was ported to GPUs last summer as part of my master thesis work. It is implemented through this GPU computing library called TUBI, which I wrote last summer for specifically this work. It's C++23 library. It's implemented through Rock Trust for AMD GPUs. In the future, we plan to, when we need to have NVIDIA backends or CPU backends, we can use different implementations of the Trust library, and we hope to have easy ports, but we cross that bridge when we get there. And this TUBI library utilizes MD-span, which comes from C++23 standard library, and it helps us handle multidimensional data in C++. Here is example code of this TUBI library usage. Here in the first line we define the grid type. I commented this out. This would be long, like couple lines, so this is a slideware, but here we would specify that in this example we want 2D grid of 3D vectors. Then we can create, let's say, 16 by 16 grid. We can take MD span to that grid, create this MD grid work object, which is basically like a work queue. We can call for each index, give the MD span to it, and then this lambda that takes two arguments, IDX and JDX, and the IDX goes through the grid indices, so the 16 by 16 indices, and this JDX goes through the, as there is three-dimensional vector on each grid point, it goes through the indices 0, 1, and 2. And under the hood, the data is stored in contiguous memory in such a way that the layout makes sense and it's efficient, like cache efficient. And this library helped me to port the code much easier. Current performance of the GPU accelerated Rungo, we use this push time metric, which is basically the number of GPUs times lap time divided by number of particles, so we can a little bit compare different simulation sizes. And we target this push time to be below 10 nanoseconds, but currently we are in the range of 60 nanoseconds with 4 particles and 200 nanoseconds with 32 particles. So it scales badly with number of particles, and we know that the particle communication is the slowest part, so this is something we have to work optimize in the future, and this is what I will be focusing during this spring. Here is different components of the simulations. Here on the x-axis there is the number of laps, and on the y-axis is the push time in seconds. And the most important part is here that the total time is here, and the particle communications, you can see it takes a significant part of the simulation. So optimizing that is our highest priority at the moment. Then I use this filamentation instability as a physical test case for the GPU pod. So because then we can derive theoretical values for this filamentation instability growth rates, and then we can do the simulations of the filamentation instability, get the growth rate from there, and then we can compare it to the theoretical values and get a confirmation that the simulation actually gives physical values. And this filamentation instability consists of two counter-streaming electron beams with some number densities and coordinate velocities. Immobile ions are considered to neutralize the plasma, and they are immobile, so we don't add them to the simulation, but theoretically they are there. And initially the system is current neutral. And this is somewhat misleading. The beams are not they are basically on top of each other. They don't collide at some point. They start on top of each other, and then the instability develops. And the wave vectors of the unstable modes depends on the temperature, velocity distributions, and initial flux velocity, basically. But you can do some theoretical mathematics and get you can linearize the Vlasov-Maxwell system in cold fluid limit, and it yields this dispersion relation for angular frequency omega and wave vector k. We don't have to go into the details of this, but basically solutions of omega and k from this dispersion relation describes the allowed wave modes in the system. And if the imaginary part of the omega is positive, then the waves grow exponentially. So we get the instability. If we have symmetric beams, we get quite nice form of this x. Here is basically the omega, but it's a dimensionless unit. But it's the details, so it doesn't matter here. But what matters is that we get this nice analytical expression for the growth rate of the filamentation instability. And here we see that we simulated the colorful plots are what we simulate, and the dashed lines are the theoretical values, and we can see that we get quite nicely the correct ones. Conclusions are that we have the GPU port working, and we verify that it works. We have to optimize it further, and then in the future we will implement more features with complex boundary conditions, squiddy effects, and curvilinear coordinates. Thanks.
Excellent time. So let's see if we can get this working. Yeah. So do you have questions for Miro?
Thank you. Question about the number of particles per cell. I'm not sure if I missed it, but what sort of a number of particles per cell are you aiming at?
So basically, the first simulation that we the production run we are planning to do is about this specific system. I cannot remember the name of it at the moment, but I think we are aiming for 4 to below 10 particles per cell. But then you can of course increase it, and depending on the system. But depending on what kind of simulation, what are you simulating, it depends.
Okay, good. Any further questions?
Thank you. What's the definition of the lap time here?
These laps are basically each time step.
Okay.
So one each lap we call time step laps here. So yeah.
Okay, we still have time for questions.
For the talk, I wanted to ask about the ion, because you tested the simulator on basically it's electron counter-streaming setting, so it's basically electrostatic limit, right?
It's the setup is such that we take really cold Maxwellian, relativistic Maxwellian, and then their context stream, and like they are identical.
Yeah, but if you're considering immobile ions, that means that you will have only electrostatic interaction, isn't it correct?
There is because filamentation requires it's electromagnetic. You have it develops in electric field and magnetic field, so that's good test for this.
Mm-hmm. But when you simulate, and you still simulate in Maxwellian distribution, like you still sampling ions.
No. We only have electrons in the system, like the particles, electrons, and then we have the electromagnetic fields on like a grid, and then we develop them using Maxwell equations.
Mm-hmm. Thank you.
Okay. Still one more question? Okay, if not, we thank you again.
Okay? Yeah, getting there. Better. Yeah, it's very.
I think if you walk ahead a little.
Yeah, then it's. Okay, let's see that. Yeah.
Okay, the next speaker is Mark Alho.
Thank you. Okay, this is going to be a bit less in detail presentation. I'll give an overview by showing a couple of cases that we have been looking at with Glaciator to support the Plasma Observatory proposal, and then I'll start with just giving an overview of the Plasma Observatory concept first. So, to begin with, why do we need this sort of thing? So, as Alessandro was already overviewing a bit of presenting the Plasma Observatory, repeating a bit of that. So far, we have this observational gap in the plasma physics of the magnetosphere, as MMS and cluster constellations have been doing multi-point observations, but at only one scale at a time, so we can access spatial gradients at say fluid or electron or ion scales at a single time. But we know that energy is transferred between scales in plasma, so we would actually need multi-scale measurements, which would open up quite a lot of interesting science in the system. And how would we do this? So, well, the simple solution to get one scale of gradient resolved is to use a geometric simplex, so this tetrahedron with 4 points. And then if we add another tetrahedron at a smaller scale, say, then we have well, 2 tetrahedra here, and if we share a spacecraft then between these 2 tetrahedra, then we are good with 7 points. And of course, if we have seven spacecraft here, this will span quite a lot of other tetrahedra. So there's actually 35 tetrahedra that you can construct from this constellation. So this can be a bit of a larger data assimilation problem. And that's something that we'll be looking into. And how then we are supposed to measure what is the actual realization of this sort of multi-scale concept, this Plasma Observatory. So PO for short, or you can also encounter this acronym PMO, which the legend says is because the ESA systems require 3-letter acronyms. So that is an explanation for that. And this is an M7 mission proposal. It's on its last legs in this study phase, and the proposal is going to be submitted soon, and decisions will be coming this summer, so it's a bit busy time here. And this is kind of the overview of what sorts of science questions there are. And there's two themes of how particles are energized in plasma locally, and then how this whole system globally transports energy and drives these sorts of energy multi-scale coupling processes. And the mission is going to be focusing on these key regions, so Borsuk, Dayside magnetosphere, basically, up to the magnetopause, or down to the magnetopause, and then in the tail current sheet and transition region, which have a lot of instabilities going on. And it's based out in 3 different science phases with different scales for the tetrahedra, keeping this sort of 1 to 5 scaling between the inner and outer tetrahedra, so that we can access, say, almost electron scales in the tail and ion scales at the same time, or ion and fluid scales, and in between. Because of the orbit, the tetrahedral constellation is going to be good at the ends of the orbit, so that's kind of focusing then on these regions. And there's a nice feature of this plan is that the instruments are going to be identical over the constellation, so we'll get 7-point measurements with the same instruments in magnetic field, electric field, and also then what is rather cool in terms of Glaciator results as well is that there's going to be the novel plasma camera instrument that is going to be giving full velocity distribution functions at quite high cadence. So that is lengthy enough to resolve ion dynamics at really multi-point, multi-scale way. And then how have I fit into this system? So the proposal, this is just one flowchart. Presentation is always interesting. So the main science study team is quite small, but then there is a bunch of different working groups that are kind of the community involvement, with numerical simulations working group that I'm leading with Takka, and there's multi-spacecraft methods group with Giulia Cossani, Alexander Chasabis, and so on. Several of these, and nowadays also one early career network with Simon Leutenbach. So early careers researchers are really welcome here. And to say a bit about the simulations working group, which has this sort of acronym Gianni for the late Giovanni Lopento. So the modeling working group is it's this rather large collection of modeling groups or modelers, and so far we range pretty nicely from local simulations to truly global simulations, from fluid scales to ion and electron scales. So we are covering a large gamut of physical models here in this working group. And then, how does Glaciator fit into this? So Glaciator is the global hybrid plasma model of Earth's magnetosphere, University of Helsinki, and Milla Palmroth is the PI. And the goal of this is to have the global dynamics of the magnetosphere while resolving the ion scale physics. So we get, for example, in the tail, we get all sorts of ion kinetic instabilities going on, and we can then resolve those. Should be actually moving. Yes. One of the nice features here is that the IMPDs are in the Blasov description, so distribution functions that are propagated by the Blasov equation, as nicely demonstrated by Miro, or described with this Blasov equation. But this is a noiseless method, so there is no particle sampling noise in the velocity distribution functions, so we can get really accurate gradients. And electrons, well, we don't care that much about those, at least yet. And in some detail, so we can focus on the magnetic tail dynamics a bit. One thing that we have been looking at a lot, and especially Lauri Pankalainen has been looking at a lot, are these bursty bulk flows in the magnetic tail. So these blocks here, so these are regions of return flow from the tail going towards the Earth, which are associated with these dipolarization fronts. And yeah, these are inherently three-dimensional structures, so it pays to look in a larger context, the surroundings, so that would be, for example, the outer constellation of Plasma Observatory. And then the inner part of the constellation would focus on the velocity distribution functions. As we can see here, the nice thing about oscillator is to access all of these. So these distribution functions are now sampled along this line here through this BBF. And we can see that developing quite smoothly there. And from these distribution functions, we can derive the plasma moments at high accuracy, and we can get gradients of those as well at rather high accuracy. So really getting into the details of the how of particle acceleration. And then the 3D structure of the BBF can be then considered like the context what is driving this process. And here, as an example, here's another time state of the same simulation as shown before. Here, the small black dots are a plasma observatory constellation just overlaid on one of these. These are ballooning interchange beds, most likely. And on the color scale here is this pressure strain interaction pi d term, a term that describes how bulk flow is converted into thermal energy or vice versa. So that is coming from the moments and pressure terms and the gradients of velocity. So here, for example, we can resolve this structure here in this pi d with this plasma observatory inner constellation, and then we can see what is actually happening around it. So is it now a jet or a continuous stream or what have you. Then further, another thing that a student of ours, Loikkanen, has been looking is some of these advanced multipoint methods. So, well, if we take the old calorimeter technique for one tetrahedron, that will get you current. But if, in case of 7 points, yeah, 35 tetrahedra, that sounds a bit tedious, but there are other ways of doing this. So, for example, Broren et al. Had this review paper of several multipoint methods, multipoint being like more than 4 points here, including radial basis functions, which is a rather general way of interpolating and extrapolating fields from point measurements. This study was done in solving turbulence, or model of it, and we wanted to look how it works in the magnetosphere. So let's say we have here a constellation, and then we have some covering region of the constellation. It is a bit extrapolated outwards. And in the context of the original study, this Broren et al.,
there, because it was solving turbulence, the Taylor hypothesis is good. So you can assume that the plasma structures are flowing past that constellation, and then you can actually extend the time series to cover a larger volume, even with even more points. And this method also handles this sort of a situation very well. But of course, the Taylor's hypothesis is a bit of a stretch for the magnetosphere, or at least it can be. But looking at how well does this reconstruction then work, just finding some flux rope here and throwing this sort of constellation around in the data, and we can see that yes, we get the flux ropes. There are magnetic field lines here, blue from Lasier to red from the reconstruction. So yes, there is a flux rope, that's good. But if you want to get into the details, comparing these reconstructions isn't quite trivial. If you take pointwise errors, those can be off by quite a lot. Because if the structure is a bit offset, it will be kind of wrong everywhere, but it still captures the whole, or the idea of, or the structure in general. So for that, there's been some looking into how to compare distributions of the magnetic field components, for example, in this case, and that gives us a goodness of fit. And then we can use this to look at how much the reconstruction is suffering from if we are missing some spacecraft or a whole part of the constellation, and how much it is sensitive to orientation of the flux flow with regards to that trajectory. So, yeah, one thing that really we want to look into more detail is here, the Taylor hypothesis, because the structures can evolve, and to see if we can actually look, try to mitigate that somehow. And that's kind of the next step in this, beyond providing these sorts of estimates for the actual proposal. Then further, because the Plasma Observatory is not going to have any visual cameras, so no selfies of the satellites, which is good for PR, we can kind of supplant that with the 3D simulations. So if we want to be able to show and not tell what we are doing in this space physics that is really not visible. So 3D data is really good for that. And here, as an example from a recent Lasier run, a flux slope on the dayside magnetosphere, magnetopause, with some reconnection lines sprinkled around here, some flux slope actually is more here, Kelvin-Helmholtz instability going on in the magnetopause, so there's lots of things happening here. So this is a nice striking example that has still some rough edges somewhere, but could be nice to have. And one thing that I really want to do is try and get some interactive viewers online, because everything is online nowadays, so why not put some 3D model like this with a bit of a story behind it. But okay, here we have the Plasma Observatory and we are observing now this flux slope. So, thank you. That's about it.
Thank you very much. There's a very quick question for Mark. If not, you can catch Mark during coffee break. So thank Mark again.
Hello.
I think it's better to use this one.
All right,
Okay, can you put the slides now? And, yeah, the next speaker is Urs Janse. I'll hand this to you.
All right, while they're still setting up, I can start talking. We are continuing with the Glaciator Research Group at the University of Helsinki. Marco gave a quick but pretty much complete introduction. I suppose everybody has at least enough knowledge of what Glaciator is now, since it's got mentioned all the time. And we're moving now further inwards from the magnetosphere to the ionosphere, as soon as that's come up. Because so far in the history of Glaciator, first we were simulating the outer magnetosphere because that went well, and then we moved further in, and within the last 2 years or so, the Glaciator code has been integrated with a ionosphere model in order to couple with the ionosphere dynamics and see what we get out from that. Yeah, sure. I can keep talking without slides. Yeah. So from the point of view of the simulation, we have this inner thing, the inner edge of the simulation, and that is our ionospheric boundary conditions. But of course, from the point of view of the scientists that look at geospatial data, that's the most important thing there is. This is not the PDF or the, yeah, that's the PDF. Okay.
Sorry,
Yeah, sure. Which means that. As long as we get it full screen, I'm happy. And so I'm going to talk about what it's doing and how it's working and how it's developing in the near future. This is a very similar picture that Marco showed on the previous slide. This is what a typical Glaciator simulation looks like. We're simulating Earth magnetosphere. So as opposed to the first talk of the session, where we were talking about relativistic plasmas, we are in a very comfortably non-relativistic regime because we're simulating the solar wind as it interacts with Earth. The outer size of this box is, you can imagine, about the size of the moon's orbit. We're not simulating the moon, but that gives you the length scale of it. And we are one of Finland's top supercomputing users, so the big machines in Kajaani, for example, are being kept warm in the winter by running our big simulations. But specifically, you can see in this picture that there's this tiny little sphere in the center, and that is Earth. And in the past, so up to 3 years ago, what we were putting there was simply a perfectly conducting sphere, or we assumed we had a bug, it was never a perfectly conducting sphere. But in any way was not a good model of an ionosphere because it was just swallowing the plasma as it fell in. And we decided to do better than that. So we implemented a ionosphere model that's more or less run-of-the-mill industry standard. We were talking to the GUMIC simulation group at the Finnish Meteorological Institute and implemented a model that is pretty much working on the same design principles as that. Namely, we have our ionosphere in the center of our simulation box, and we just put a triangular grid on that sphere, and say for every element of that grid, so for every little triangle there, we follow the magnetic field lines of our dipole field up until we encounter the innermost simulation cells of our loss of simulation. And we just say that everything that flows to that upper triangle then follows the field lines down to the lower triangle. And that way we can establish a two-way coupling between the magnetospheric model that is the Vlasov simulation and the ionospheric model that has all the complex ionospheric dynamics going on. Which gives us then inputs like the field of light current system, the magnetospheric plasma dynamics causes currents along the field lines, and we can directly map from the magnetosphere to the ionosphere. Now this is a typical look onto the North Pole of Earth's ionosphere, and you can see 12 o'clock, so the sun is that way, and typical current dynamics here. And we also get other quantities mapped down, like plasma density, plasma temperature. Here we have electron temperature. You can see that the primary peak of electron temperature is here, where the magnetic field lines connect to the solar cusp. And that's all nice, but then we want to solve the actual ionosphere dynamics, and now here comes the first problem. Because we need to get somehow an electron distribution function to model what is the spectrum of electrons that are precipitating. But if you've been paying attention in the previous talks, Markus said it quite succinctly that we don't care about electrons. Our simulation does not carry electrons. We only have a velocity distribution function of the ions in the velocity simulation. And so what we do is we do the simplest possible assumption. We assume that our ion density matches the electron density and that our distribution function is Maxwellian, matching the temperature of the ions with a factor 4 that's very badly empirically motivated. And then we get a precipitating energy spectrum of electrons, and that's about as good as you get by doing these assumptions. The operational MHD simulations from FMI do something similar, and there it's okay because it's an MHD approach. You assume that your distribution functions are Maxwellian, and then you go with that. But doing kinetic simulation, you would really want to do something more consistent with itself. Anyway, we implemented that, and it runs, and it gives us profiles for electron density. At every point of our ionospheric mesh, we can now, over altitude, look at what is the electron density received compared to literature. This is from the Shokunagi 2009 ionosphere book. You can see that we're nicely reproducing the lower altitude ionization peaks and then reproduce ionospheric dynamics based on that. But then it so happened that next door from us in Kumpula, there's the Finnish Meteorological Institute, and Lisa Juusola, working there, has trawled through a large history of iSCAR radar observations and correlated them with image magnetometer network data. The image magnetometer network, if you don't know, is a network of stations in Northern Europe that measure magnetic field fluctuations, and the magnetic field fluctuations are obviously being caused by ionospheric current systems, so you can infer from the magnetic field or the deviation directions what is the current system overhead in the ionosphere. And at the same time, the iSCAR radar with an emitter in Svalbard and then receiver stations in multiple points in Northern Europe allows you to measure the conductivity and radar reflectivity of the ionosphere that results. So this study went through many years of this data and correlated the observed conductivities with the current systems that were observed. And one result that stood out there and interested me immediately is it turned out that if you take the current density of the divergence-free current, so only the curl of the current in the ionosphere, that is a kind of good predictor for the Peterson and Hall conductivity, the height-integrated conductivity in the ionosphere. You can see these are scatter plots over, I think, 20 years of measurement data, where some of the, especially the high current density outliers, are all over the place, but by and large, they form a relatively nicely collimated scatter plot there. And so this model fits an analytic curve through that, and if you have an idea of your divergence-free current system, that also gives you an idea of the conductivity, without the need to assume any electron distribution function or any sort of atmospheric model at all. So that is very nice. The idea thus was we just take the divergence-free current system from the simulation data and use that as our proxy for our conductivity. So how do we get divergency in plane currents if all we have from the simulation is the field-aligned current? We have this magnetospheric simulation somewhere out there, and we have this little sphere in the center, and somehow we want to know what is the current system on top of that sphere. So we know the field-aligned current coming in from the magnetosphere. It hits the sphere and it will not be absorbed. This current needs to go somewhere. So, of course, the field-aligned current will correspond to the divergence of the current on the sphere. So that gives us the curl-free current system, because now this is divergence. The Helmholtz theorem says that every current system can be uniquely decomposed in a curl-free and a divergence-free system. But we also know this is a field-aligned current, so it just came along the field line, and when it hits the sphere and goes perpendicular to the field line, it will have to have some sort of Hall effect. So there will be a current system also forming by the Hall effect perpendicular to this current direction. And now the question is, what are the magnitudes of these relative to one another. And by a stroke of luck, the same statistics from the user et al. Paper was done comparing this parameter alpha, that is the ratio between Hall and Peterson conductivity, so the ratio between conductivity parallel and perpendicular to the electric field. And that approximately also corresponds to the ratio of current-free and divergence current caused by a single field-aligned current element. And as you can see, this very strongly clusters around 1. And by a very good approximation, we can just assume this to always be 1. And that makes a wonderful model, because now we can simply say that curl of J on our sphere corresponds to the field-aligned current density, and that gives us a divergence-free current system. So we implemented that. And now we can compare the resulting conductivities that we get from the old model with guessed electron distributions and the new model, and I apologized, here the coordinate system is flipped, so now 12 o'clock is to the right, sun is over here now. The overlaid red and blue outlines are the field-aligned current densities coming in from our magnetic effect simulations, and the green-bluish colors are now the conductivities. And you can see there are some qualitative differences between the two. One is that the old model was overestimating the conductivity in the tail, the new one is less conductive there, but also that there's now a much more enhanced conductivity in the morning sector here, which corresponds better to observations. So we are very confident that we actually did an improvement here. Once we have the conductivity and our field-aligned currents, we can solve the potential on the sphere, and we get all the wonderful ionospheric observation quantities like the cross-polar potential and so on. So then we have the overall current system solved. We get our potentials, we get the incline currents, and we can derive all kinds of ionospheric physics quantities like ohmic heating and so on. And here now we have a comparison of the potential map from one of our standard setups. We simulate a solar wind condition, fast solar wind with southward interplanetary magnetic field hitting Earth, 750 kilometers per second speed, 10 nanotesla magnetic field strength. The old system gave, or the old implementation gave a somewhat symmetric profile. The new one is much more asymmetric, and if you compare that with a statistical data set from the SuperDARN radar, that actually looks quite similar to what our new model now produces. It's a bit not a surprise, because the SuperDARN radar model is also curated by Lisa Lusor, but still it gives us confidence that what we've implemented there actually gets us a step into a much more physical ionosphere model. So coming to the conclusion, we have with our big supercomputer simulations now the ability to produce ionospheric maps of all kinds of quantities. Here's an example that I'm particularly proud of, because the first time it worked, I just plotted J.E, so that's ohmic dissipation of energy in the atmosphere, which I plotted in a color scale that looks like aurora. It's not exactly, there would be some photochemistry involved, but you can see that the peak of that, when mapped onto Finland, sits exactly where you would expect aurora. So this is looking good, and you can expect lots of nice ionospheric science output from Blase ITER in the near future. Thank you very much.
Thank you very much. So finally, do you have questions for us? I could ask, if you do like a similar run that you did with Glaciator with this new ionospheric setup, if you do a run with some cheaper local MHD model, would you get different result or not?
Well, most importantly, the features that we see in our ionosphere, and what we really see as a difference to the GUMIX MHD model is, since Glaciator is a kinetic model, we see much more wave instabilities, much more complex dynamics of the magnetotail, and already with the old model we saw there ionospheric signatures of, for example, these vertical flows, for example, any kind of instabilities going around. And now that this new model is actually working, it's going to be up to the team to work through the phenomena that we studied so far and compare how does it look with the new model, how does it compare to observations. But we definitely see much more fine-grained and much more interesting effects moving around the ionosphere compared to MHD models, simply due to the fact that we have much more dynamics covered.
Any more questions?
The input field line current data that you're using to drive the model, where does that come from?
So the field line current data from our simulations comes directly from the magnetospheric kinetic simulation, but the data set that went into this Ursula et al. Model to actually create the mapping between the divergence free system and the connectivities, that was image magnetometer data of the last 20 years or so. So that was the entire set of data points measured in the Nordic countries.
Okay, so yeah, we need to move on for the next presentation, so it's time to close again. We have Fabio. Okay, let's see if the presentation comes up.
Hello everyone. I'm Abhiyat, postdoctoral researcher at the University of Helsinki. So, the title of my talk is Effect of Ionosphere on the Magnetosphere in the 6D Blaziter simulation. So, these are the outline of my talk. So, I will briefly talk about Blaziter, but it's already presented by Marco and Ursula. I will not go through that. So, but I will briefly discuss the magnetosphere-ionosphere coupling scheme in the Blaziter simulation, and then I will talk about the motivation of this ongoing study, and then I will present some of the initial results from our simulation. It's already presented, but this simulation is from the first 6D magnetosphere simulation with coupled ionosphere. So when I say the effect of ionosphere on the magnetosphere, I'm trying to see if the ionosphere where situated at this point is now, if it's affecting the dynamics of the magnetotail, for example, in this wavy dynamics of magnetotail. So, we are not going to go into detail how this dynamics is affected by the presence of ionosphere, but I will pick some parameters and see if the presence of ionosphere in the simulation affects some of the basic parameters in the magnetosphere. Okay, so as Urs already presented, the ionosphere in the Blaziter is modeled as a thin spherical shell at about 100 kilometers above the Earth's surface. So the coupling between the ionosphere and the magnetosphere is made in such a way that the field align current in the magnetospheric domain is calculated at the curl of P, and that field align current is now down mapped to the ionosphere together with the density and temperature of the electron density. And then this electron density, temperature, and field align current are now used to solve the ionospheric conductance, horizontal ionospheric current, and then electrostatic potential. once this is solved, then the electric field is then calculated at the gradient of the potential and then up mapped to the magnetospheric domain so that it will affect the dynamics of the plasma in the magnetosphere. So what's the motivation of this study? So the model, the ionospheric model is still in progress, but we are still testing, for example, how the ionosphere is affecting the dynamics of the magnetosphere. But recently we have studied the ionospheric signatures of the plasma, these burst bulk flows in the magnetosphere. So in that study we have found that whenever there is this burst bulk flows, the field align current, region 1 and region 2 field align current, the ionosphere also enhanced. The conductance also in the ionosphere is enhanced, and even the horizontal ionosphere is also affected. So this showed that the dynamics of the magnetosphere strongly affects the dynamics in the ionosphere. So the question is then, did the ionosphere also do the same effect on the magnetosphere or not? So that's our motivation here. So as I've said, the question is that now, if the ionosphere responds strongly to what's happening in the magnetosphere, does it really, the ionosphere affect also the magnetosphere in the present 60 blaziter simulation? So to see this effect, what we do is we take two simulations, one with a coupled ionosphere and the other with an inner boundary. So that is no active ionosphere where the electrostatic potential is coming from. So other than that, the two simulations are the same with solar on the speed 750 km per second, MEF PZ southward 5 nanotesla, and the solar room density 1 centimeter per here. So the first test I did is I have compared. This is now the non-coupled simulation. This one is the coupled simulation. So as you can see, this is actually on the equatorial. No, this is a extended plane. So I have compared the air-to-air plasma flow velocity Vx in both non-coupled and coupled case. As if you see closely around, let's say 11 or 12 RE, so this air-to-air plasma velocity increase at, for example, it reaches even maximum at this point. Instead of comparing this visually, so what I did is I take, for example, the Vx within -10 to 7 RE on the equatorial plane, and between -2 and 2 in the Z direction, and then compare that average value between the non-coupled and coupled case. So this shows that with 500 simulation times, the average L2R speed is much greater in non-coupled case than the coupled one. So indicating that the ionosphere is actually reducing the velocity of the L2R plasma velocity in the magnetosphere. Same thing. So what here we did is I also compared the cross-tail electric field between the two simulations. Here again, this is the non-coupled case, while this one is the coupled ionosphere, and this is just the difference between these two. So again, when we take the average of the electric field, this cross-tail electric field, we have found this strong difference between the non-coupled and coupled case, where again this showed that the ionosphere dampens the cross-tail electric field. So the next, so I have also compared the cross-tail current, sorry, here. And this is now, the current is now flowing into in this case, so the cross-tail current is here, so it's flowing into the board. So what I did here is also, I integrate the cross-tail current between minus 25 to 7 RE and between minus 2 to RE, and we have found that in the coupled ionosphere, the cross-tail current, the integrated cross-tail current is still again lower than the uncoupled case. Still, so that it shows that the coupled ionosphere weakens the cross-tail current system. So one last thing, I have been, still it's a work in progress, but I have also tried to see how the coupled ionosphere affects field aligned current system in the magnetosphere. So for example, here is the X-8 plane. So I'm just focusing now on the night side of the magnetosphere. So as you can see, for example, there it is into the magnetotail and to the ionosphere flow of current in the non-coupled case, while in this case, for example, there is no almost single layer field aligned current flow. So overall, compared to the other parameters, the effect on the field aligned current seems minor, but still there is some difference. So in summary, so we have found that the coupled ionosphere modulates the K magnetospheric dynamics in our 6D simulation. So we have seen the reduction in the reservoir plasma bulk flow, cross-tail electric field, and also cross-tail current intensity, while there's a small modification pattern as seen on the field aligned current. So for future, so as also said, we are still developing the ionospheric model, so we are going to test the sensitivity of this result by running by incorporating different ionospheric conductance models and to test the sensitivity of our results. Yeah, thank you, that's all.
Thank you very much. Excellent timing. You have questions for Abir? Seems that people are waiting for the coffee, so we can catch Abir during the coffee break. So okay, sorry. So there's an online question. Yeah. There's one more presentation, so don't we get? So yeah, let's thank Abir again. So we have set in Dewberry as presenter.
I'll run you through the context fast, then I'll show you some open questions, show you even fewer answers to those questions, and then talk about what can be and what should be done to answer the rest of the questions. So, what do we see in the context of electron acceleration? We have, for example, in situ measurements from plasma instruments and particle instruments showing accelerated electron populations in congruence with shock observations, and these are of course then affected by connection to, for example, the sites of the coronal shocks originally, and the picture is not clear in situ measurements always about what's going on with electrons. Another good thing about electrons is that we see radio bursts in connection with shocks. A very brief description about radio bursts. You have a dynamic spectrum of radio emission. You have frequency
on the y-axis and time on the x-axis, and then you have the intensity of the emission as a color gradient. And then you see these different kind of structures in the dynamic spectrum. These different types of bursts, they're numbered from 1 to 4 in this graph, then correspond to different kinds of acceleration processes or other electron processes in the solar corona. And going back to the observation plot, you can see kind of a vague line that curves, and that would be, again, a type 2 burst here. The y-axis is flipped, which is sometimes or usually done in the context of these radio observations. So these type 2 bursts in particular are then connected to electron acceleration in shocks. And how they are born is, or how the radio emission is born is a complex process, but I'll focus on the electron beam itself. So, how to then, we do see accelerated electrons, and we do see this radio emission connected to accelerated electrons, and we understand that process theoretically. What we really don't know is what or how the electrons are accelerated, what kind of a plasma parameter space or shock parameter space is what produces these energized electrons. There are a couple of theories on how electrons would be accelerated, and these are all related to, well, charged particle acceleration in general. I'll quickly explain it through these graphics. So we have time on the y-axis, so as time moves forward, when the particle moves up, then moves forward, and then we have position, and then density is now what is describing the shock itself in this case. I'll start with diffusive shock acceleration, which is kind of, at least for protons, the established or considered the main acceleration theory for protons, and quite well researched and also understood. The particle travels to the shock or through the shock, can interact with the shock and be energized in that. It can travel through the shock or be reflected at the shock, but what makes diffusive shock acceleration efficient then is that that particle can scatter from fluctuations or waves in the plasma and then end up again to the shock and repeat this process over and over again. Another theory quite established is shock drift acceleration. Here the particle arrives to the shock, usually in very perpendicular cases of the shock. It kind of traverses along the shock surface for a bit, gets energized there, can be reflected or passed through, and then does not interact again with the shock. Both of these theories have their issues with electrons. So for thermal electrons in the solar wind and in the corona, diffusive shock acceleration is not efficient enough. The timescales are not long enough for electrons to be energized at the levels we see. And then shock drift acceleration is limited in the maximum energy it can give to the electrons during the process. So then a combination of these two in practice has emerged recently as a theory, where in practice now you're doing shock drift acceleration, but you're repeating that process again by keeping the particle trapped in the shock transition region. And again, it's assumed that there are some waves or fluctuations that keep the electron at the shock transition region. Now then, I'll go to the modeling part. So again, we're not sure about the mechanisms or what the parameter space really is, what controls this. So we need to investigate that. For that, we have a one-dimensional Monte Carlo model. The one dimension is now along the shock normal. The shock is at x equals 0, and we're in the Hofmann-Teller frame to get rid of the convection electric field in the simulation. We have a finite shock thickness, so we don't assume a discontinuity as electrons experience the change more drastically in the shock, or actually less drastically because of less inertia, and then the electrons will see the transition of the shock instead of seeing a discontinuity, as you could assume more for protons. We have the upstream and the downstream, and again, as we're in the HDF, the plasma flow is along the magnetic field lines. And then we'll have our Monte Carlo test particles, each with their speed and a pitch angle cosine and position and whatnot. In addition to this, the simulation box has a finite size with free escape boundaries in the upstream and downstream, which is relevant for the processes in plasma so that we're not leaving the particles in the box being practically stuck forever. And then about the shock that was now then simulated for this, it's a coronal shock. These type 2 bursts are most associated with coronal shocks, so it's an easy case to choose. The parameters are general parameters, so not based on any one particular event. We have a fast shock. We have a typical Allen speed in the corona. We have a very perpendicular shock for the first part of the investigation. We have a coronal plasma temperature and the density. And then in the first part, the particles are injected monoenergetically at 1 keV, which is a bit above the median of the thermal population. Otherwise, you can see the transition of the shock. It's a hyperbolic tangent profile. The obliquity, which is correspondent to the magnetic field strength, is it increases through the shock. And then to keep HDF throughout the simulation, the flow speed profile is chosen ad hoc in this case. And also the mean free path of the particles related to this scattering process is also ad hoc. So instead of modeling the waves, for example, self-consistently, which is computationally expensive, we're choosing to use an ad hoc mean free path profile to also kind of investigate what would be the controlling mechanisms in particle acceleration. So I'll kind of start with what DSA is. DSA is simulated in a large box so that the particles have enough space to be scattered back to the shock so they don't escape the shock immediately. And then different kinds of mean free path profiles are tested. So the black case would correspond to traditional DSA. And then the other cases would be something more along the lines of SSDA, with the yellow line being kind of the limit set by the original papers. DSA produces accelerated particles in this case quite well actually, but again, we are assuming a homogeneous plasma and a constant shock for over a period of time or distance in this case, which is not realistic in all senses. So the timescales are most likely too large in the demonstrated simulation here, but it works as a test case to show that a power law distribution is produced, which is what we expect with DSA with enough time. And yes, we have separately the upstream and downstream escaping particles, though the upstream particles are now a bit more of interest in all cases. Then not much of a difference can be seen between the black and blue curves, other than that the maximum energy is changed a bit, and then of course this increased scattering at the shock smoothens out the distribution more. Then something drastic happens once you drop the mean free path to the red curve level, and simply put, the particles are affected through the shock and cannot escape the downstream back to the upstream anymore, and practically have a single interaction with the shock, which does not end in a huge energy increase at all. So no particles escape to the upstream anymore in this case. And the yellow case is similar, but even more drastic. Simulating then shock drift acceleration, you can see now that the black curve, which is the SDA case without any kind of reductions in mean free path, does provide an increase in energy from the 1 keV to roughly 10 keV, but not more than that. The blue curve again is similar to that in the case of DSA, but now very different in the case of SDA, indicating that there would be a point in well, assuming that some processes, at least described by SSPA, with some parameters would be a good idea. And then again, the red and yellow curves cause this advection problem for the particles, so that they're simply pushed through the shock. Now I'll say at this part that the choice of the profile of the reduction at the shock does affect this, so having a wider profile would most likely be more beneficial. But this mean free path profile was assumed to then be in correspondence with the gradient of the magnetic field in this case. Alright, I think. Then back to the radio burst generation. So I mentioned that we're looking for a electron beam, and that was done by injecting a Maxwellian population. So now we're really using a 2 million Kelvin electron population, and then we're varying the shock obliquity to see when the electron beam, if generated, would be generated. So starting from 70 degrees, quite a perpendicular shock already, does not seem to generate a beam. You do have this bump on the blue curve on the right, which is now the kind of parallel momentum of particles propagating away from the shock towards the upstream, which is also the bottom left plot. But now instead of slices, you have this whole gradient. Moving on to higher obliquities, you start seeing the beam develop a bit more, but it's not really detached from the original Maxwellian population. And then going to higher perpendicularities, you start seeing the beam kind of residing in the tail of the distribution, and then which could then lead into the generation of the radio burst itself. Okay, that's enough results then. So all of this now is a part of this model easy. All of the plots and simulations themselves are a part of this model. It's made, it's an open source model, and it's made to be easy to use. It's documented well and meant for general use as a model. And otherwise, what else is being done with EASY currently is that we're also investigating electrons into the context of bow shocks, in this case the Earth's and Venus's bow shock, and then other kinds of shock geometries or magnetic field geometries are of interest. So these closed magnetic loops, for example, in front of shocks cause also particle traps and could result in very different looking electron populations, also when then assuming, for example, perpendicular diffusion and whatnot. And then this radio burst generation itself should be investigated, for example, using a three-way model, a simple approximation of how these Langmuir waves then decay into the radio emission itself in the end. I'll conclude there. Thank you.
Okay, thank you very much. Do you have questions? Okay.
Yeah, thank you very much. That was an interesting presentation. I was wondering about your scattering model there. I mean, you showed your mean-free path parameterized around the shock, but what kind of a scattering model did you use? Did you just then randomize the particle pitch angle, or did you do small angle scattering, or do you have any good motivation about what kind of scattering you would expect at what location?
So the model itself is stochastic small angle scattering. It's an easy assumption to make, again, in the context of DSA. It's an easy comparison to make also. So that's what's used in the model practically. That's the motivation.
Okay. Maybe one more question. If not, we thank you again, and we thank all the speakers of the session. And let's have a coffee break so this concludes our session.
Yeah, so yeah, that's actually cool.
Are they 400 for Windows Phone? I literally know it says so. It's
Well, it asks for my address, it doesn't give my address. It gives no. Guess I'm not American enough.
Yes, there's a presentation on I assume it's it's USB-C. ionosphere and thermosphere, so effects on geomagnetic storms, on high latitude, IT coupling.
Joo.
Tuo Pamon niin tää liiva telka, koska katsotaan posistaan nyt mitäkään saa niin hyvä. No, lite obrott.
Ja, jag är inte nära textil.
Ja, ne pieteik man šitais biedri pat jāsmari pat jānštindas arī šeit.
Jā, tāpēc arī atnāca.
Jā, tāpēc es savu ir. Jānis sasakumpānis. Četri ir vārds.
Okay. Šāds arī satiks. Jānis vienais. Man tā ceturtdien jāprezentē tas pats, ko to interesē par projektu. Bet tas ir arī nosacīt arī tas doktorantūrā. Tev arī 4? Lielie?
Kā jau.
Mēs ikdienā bijām aizbraukuši septembrījus arī uz Helsinkiem, bet tas ēpasts CTPS. Tad tāds Eiroplāni kaut kāds maikais pasākums. Jā, maikais. Mēs tur bijām sarakstā vienīgie 2 Latviju. Ja to video skatām, un sarakstam cilvēku un jau vairāk Latviju vārds. Viņš tur bija, bet viņš nebūs.
Nebūs viņš?
Maz. Viņš pēc tāds. Jā. Viņš pasaka, tāpēc, ka neplāns. Man kā es vakar pieregistrējos, es pamanīju, ka viņi pareikās tā piesrakstīju. Es skatījos tajā, savu vārdus tur neatradu, piegāju, taisnu, ka man kā prezentācija. Ģēcija prezentācija ir tad, kā tur jā. Nebija. Tāpēc man pats dabūju rakstīt. Kaut kādu viņa pēdējā
Onko? Mä en tiedä yhtään, mutta
Teidän studentit saatat kuinkas pagājušajā gadā Ventspilī mācījās.
Tā Laura?
Laura. Jā.
Jo kāpīgas tēmas par to Igauniju.
Joo.
Es tikai viņu es atceros.
Jā. Viņai arī tas var kaut kāds man liekas vispār. Tuo pasar confirmada siis?
Aha, okei. Mulla on nyt se Kehä Ykkösen ja sen identian. Se on siitä sinne ihan 3 pisteen. Joo, mutta jos on vaan tuolla, niin sitten jätetään siis katoa. Menikö se takaisin VTV? Joo, se on moderatinen. Mä oon tässä Konstantin kanssa
Ja, tutto qua è tutto il bianco. C'è il passaggio per cos'è?
Okay. Welcome everyone. I'm Emmanuel. So I'll be chairing the session on ionosphere and thermosphere. I will try my best to understand. But our first talk is by Anita, who will talk about the effects of geomagnetic storms on high latitude ionosphere. Some things about this talk. So I will get up in the last 2 minutes of your given time period, so which is 15 minutes. So I assume you will be talking for 30 minutes, so I will get up at around 11 minutes.
Thanks. Okay, so currently there is a geomagnetic storm going on locally, and this talk is also about geomagnetic storms, and the basic idea that I want to compare a little bit of what is happening during a moderate storm and what is happening when we have a very intense so-called superstorm. We have studied these two different storms in several papers. So this moderate storm was in 2016, and there have been 3 publications from my group, my PhD students, about this storm. And then this famous Mother's Day superstorm on May 2024, that paper was just accepted to JGR by Leikai as a first author. And yes, so why it is important to study storms altogether is that they have very big effects on the ionosphere, thermosphere. And for example, they enhance the densities at very low Earth orbits. So let's first talk about this very moderate storm, almost weak storm. And that was caused by SolarWind high-speed streams launched from those coronal holes on the sun. And the SUM-H index, which we are using to sort of measure the intensity of the storm, was only, the minimum SUM-H was only -69 nanotesla. But on the other hand, the duration of the storm was very long. So it was at least 7 days long. And we had ASCAT radar observations about that storm by Tromsø and Svalbard radars. You can see them on the map. And the radars were scanning, so we had a large latitude span in this measurement. Oops. Okay, and then there are those several circles, and they are latitude magnetic local time plots. On the left-hand side, you can see the electron density changes during 24 hours, and on the right-hand side, how much ion temperature was enhanced. And in many of those regions where you have blue color, the electron density has decreased. This is third region electron density. And in many places, at the same places, the ion temperature is increased. But then there are, it is easy to find by eye, also locations where you do have the electron density depletion without this DI enhancement. And I will try to explain after why this could happen. And then we also have the total electron content measured by GNS receivers. That is the sort of the video on the right-hand side. And you can see the northern hemisphere, the continents. And the thing to notice is that in the polar region there is dark blue color. So also in total electron content we see a depletion. And if somebody of you spotted that the US was very red in the beginning, so that is the storm positive phase at mid-latitudes, but I will not talk about that today. There is a recent paper in JGR 2026 about that positive phase. Then I show some satellite measurements. So the top panel shows the timed buoy measurement of O to N2 ratio. And the thing to notice is the blue color at high latitudes. So this ratio is decreasing, which is telling us that, at least we interpret that N2 molecules are increasing. And then the bottom panel shows the GRACE satellite measurement of neutral mass density. And after the storm onset, the mass densities at the satellite orbit are very much decreased within the quite wide latitude range, but typically starting first at high latitudes. Okay, and this is how I try to now explain some of these things we observe. So in the top there is an equation. Theta is equal to K1, which is a coefficient which depends on ion temperature. And with ion temperature increase, it becomes larger. And that is multiplied by the number density of N2 molecules. Plus then another coefficient which also depends on ion temperature multiplied by the number density of O2 molecules. And this factor is controlling the recombination rate of O+. So if this beta is large, it means that this O+ recombination is fast. We lose rapidly a lot of ions. And then those boxes, so to start with, we have in the high latitude ionosphere, we have increased Joule heating because of enhanced convection electric field, because of enhanced electrical currents. And when we do have that heating, both the ions and neutrals are heated. So both the ion temperature and neutral temperature increase. When you have higher temperatures, you have thermospheric upwelling. the N2 and O2 molecules from the V region are lifted up to the F region, and that is something we call there's a neutral composition change in the F region. And then this box here, so then we have electron density decrease in the F region because we have more N2, we have higher ion temperature. But then we do also have, not only in the troposphere, but also at those high altitudes, we have horizontal winds and global circulation, and they can carry these composition changes to different locations. And those places we have then more N2, and again, we can now have the electron density and tech decrease even without ion temperature enhancement. Okay, so let's now then go to this superstorm. And now the SUM-H index is minus 518 nanotesla. So this was a huge storm, and that was caused by the actually very many coronal mass ejections from the active region on the solar surface in May. And now we had the ASCAT Svalbard radar observations. Again, the second panel showed a very big decrease in electron density. So practically the whole F region was disappearing during 11 May. Okay. And then I also have the total electron content video on the right hand side. There are polar cap patches going over the pole, but then you see a lot of, again, dark blue color. So again, that is showing the disappearance of F region and ionosphere at the polar region. And these observations are very similar to the sort of the normal storm. Again, we have O2 N2 decrease in the top panel, and in the bottom panel, SWARM A satellite is measuring increased mass densities. And like in my cartoon, I said Joule heating should be the thing that is driving these things. And now in our group, Heikki Vanhamäki has developed a very nice method to estimate this Joule heating. That is typically something which is very hard to measure. But with this method, we can estimate Joule heating in the whole northern hemisphere. So this is one sort of snapshot of that kind of estimation with MLT and latitude. And then in the next plot, we integrate the whole northern hemisphere and follow the time development of Joule heating. So I will show you a curve of Joule heating. And this curve is shown here, and this is for the normal moderate storm, and that was during 8 days. And there's a lot of variability. The maximum value is 250 gigawatt, and it resembles a lot of so-called level coupling function that tells us how much of the solar wind energy is entering the magnetosphere. So this Joule heating is very much now driven by this solar wind magnetosphere interaction. And then on those two panels there, I might have a pointer. Yes, here. So these are from the superstorm, and also here this Joule heating curve resembles a lot of this level coupling function. But now the value, so the maximum value is exceeding 1 terawatt compared to this 250 kilowatt for the other events. So obviously there is so much more Joule heating going on. And then I want to compare also other parameters. And this is quite a busy plot. So the first comparison is the same as in the previous slide. So basically we have 4 times more Joule heating for the superstorm than the moderate storm. And then we have estimated
iron temperature changes we have about twice, and this is quite interesting parameter. So this is the mass density at very low Earth orbit, and during the Underwater storm we see 100% increases, but then on the right hand side there are even 400% increases in mass density during the storm time. And then regarding, so this is now limited to high latitudes. At high latitudes, this total electron content reduction is about 4 times during the superstorm. If we use these physical units, DECU, if we would look at the percentages, then it would be only a factor of 2. So going to the conclusions, is that even though we think superstorms are something very, very massive and major, the physics we see at high latitudes is the same, whether you have a weak storm or strong storm or superstorm. When thinking about the numbers, so we saw that Joule heating for the superstorm was about 4 times of that of the moderate storms, and this factor of 4 came in quite many parameters. But then we classify the storm intensities by the SUM-H index, and if we compare the SUM-H indices for these two storms, then the superstorm is almost 8 times stronger than the moderate storm. So that is perhaps something I would like to study more, and to keep in mind that maybe this classification, just using the SUM-H index, is not very good describing what is happening in the ionosphere, thermosphere. So that was all. Thank you.
Any questions for Anita? We have plenty of time.
Maybe a very naive question, but when you talk about the enhanced neutral densities, is that those neutrals that will then cause drag on the satellites on low Earth orbit? Yes. Yes.
Any other questions? I had a naive question in one of these plots, in the tech plots. Okay, this one. The last panel, and the last 2 panels in particular, why does it look like, at least in that part, why does it look like some dispersive signal? Is there a reason for? Yeah, that one looks very dispersive in some sense.
I'm not quite sure if I take the mic. I'm not sure, but I'm sure about this. This looks very weird because we now, like in DC units, so anything negative is a decrease. But you see also those positive things, and in specific when we take percentages, it looks like a lot of positive spikes. So actually, those are because we have those polar cap patches. So we have sort of the background decrease in DEC, but then those polar cap patches are tiny patches that drift over the polar cap, and when we integrate everything together, so they are like that. And most likely, I have not checked what are these, but my thinking, we could also see them in the video. Also in this event, there were patches over the polar cap.
Okay, let's thank Anita once more. And our next talk is by Janis Steinberg. Again, 15 minutes.
Hi, I'm Janis Steinberg. I work at 24th International Radio Astronomy Center. I'm also the PhD student at the Riga Technical University. So today I'm going to talk about my work that using the flow station that you see here in image that we have in Latvia and in Mexico. That's how we use to study the ionosphere. So, little bit about where I come and work. So I work as I mentioned, in Ventspils Radio Astronomy Center. So besides the LOFAR, we have 2 additional telescopes. And what you see here is the frequency range for each telescope. So tomorrow, in different room, there will be a talk with my colleague, Laszlo Bezerov, who's sitting in there also here. And he will talk about more deeper about instruments and other subjects that we do. So one of the advantages that we have using multiple instruments is that we can study ionosphere in many wide range frequencies, and that allows to probe the sky in different spatial scales. So well, this is one of the things that we have a very unique situation that in Europe, the combination of such instruments as LOFAR and allowing to in the same time doing observations with L-band with same as GNS frequencies is quite a unique thing. That is something that we would like to explore more deeply and see what we can do more or differently than normally the people that use GNS receivers to study the ionosphere. So that's something that we have thought for the future. So going to further so very briefly about the LOFAR and things that you use. So what you see here is the map, and this point here is where our station is, where we work. So in another picture you see again the LOFAR station in Latvia. Then you see in Netherlands there is more stations. So this is a 6-station block, but there is more. So so we have the instrument. The instrument has there is a station all over the Europe, and each station has 2 blocks of substations. So from 10 to 19 and from 110 to 24 megahertz. So in between there are FM radio. So obviously we want to filter out that, otherwise we just have noise. So, and yeah, so not going to go deeper in here. So if you want to talk, but at me. So what we want to do is that there is a lot of correlations. So a lot of work that people compare the frequencies, that is lower frequencies below 100 megahertz, with my previous mentioning the GNS, and there is some publication. So in previous presentation you heard about May storm last year. So recently there's publication about from first author from Rebecca Ginaldi, and she explored also more things is called combined GNS and LOFAR. So that I would recommend for that publication to read very carefully. So I don't want to go to more details about this. So one of my works is I use the single LOFAR station to record the power spectra and then measure ionospheric irregularities. And one of the works that I do, that I investigate, is that ask the question: can we, with using the radio telescopes, come with a similar map that you can get from GNS, like a VTEC map or things like that? And that is one of the works that I do as my focus. So to do this, what we need a very strong source that is well defined, and what we observe is ionospheric fluctuations. In ionospheric fluctuations cause typical scintillation pattern when the amplitude of the signal varies across the time. And there is 2 sources that is very known, that is studied very much with the LOFAR, and there is those are supernova MNOMs. And then the next task is what, as I mentioned, if I want to make a map, sky map of ionosphere, I need more than 2 points, I need more points. And the big question is which sources and what sources and how to use. And that's why what we do is just do test observation to make try to think how it can involve these things. So not going more into detail. So this is typical results that we get. So this is supernova remnant, Cassiopeia A, and you see time, you see frequency, and you see amplitude, and you see amplitude variation. So, and also what you see is the RFI or radio interference. And so yeah, so what I do as a main instrument, I use standard ionospheric scintillation index S4. So it's the same as GNS. So and if we have well-known, very strong sources, as I mentioned previously, then everything works fine, and this will work well. A bit of the standard formal, but then with my colleagues such as Mike Marius, we understood that if we want to correctly use this index for radio astronomy, we need some additional corrections. We need to have very well understood the noise and the signal of the source. And this is in the bottom of time series of 60 seconds and 40 seconds of one of the source and one example. So you see S4 and second from observation. And this is one of the investigation that what I'm doing, and this is working the progress, and there's some things that I have excluded from my slides. So the next point is I combine the S4 measurements with ionospheric piercing point. It's very simple. We connect the source, we connect the telescope, this straight line, we ask where the straight line cross the ionosphere. And we compute latitude and longitude for the point that you see there in this curvature as a red point, and what we measure S4 for that specific point, and we then can create a map of sky. So provided that we have enough sightlines, if we have enough point of source, if we do this. So if we do this on all local stations that I showed the map in the first slide, then we can achieve the spatial resolution of sky maps of S4, such as comparable, such as GNSV map and similar things. And so this is still work in progress. We still want to understand if and how this is possible and how this should work at the end. So this is, you see the picture, this is one of the ideas. This is the work in progress. So there's three sources. We can track very long time. I don't want to, since I'm all running out a bit of time, I will not go very detailed of technical parts, but this is work in progress of first results from single station. So if you imagine that you would have more local stations doing the same thing, and with multiple sides of lines, then there is interesting scientific result. But this, unfortunately, is a lot of caveats, a lot of work, a lot of other things that need to be explored to fully set this to work and be very as possible as much. So this is, I believe, end of my presentation. So thank you for attention. So this is Mazda X-Plum in Ventspils, and very, as you see, very bright with all the city lights. So usually in city we cannot see this kind of beautiful images, but usually you need to go outside the city because we have a lot of light pollution. And but this is when it this is very bright, and this is yes. And I would like to be here and thank you for your attention and questions.
Thank you. Any questions from the audience? I have a question. So you, in your LOFAR, like in your plots that you showed, only the change in the amplitude. But if you consider a plane wave, you should also look at the phase, no?
Yes, that's...
because it's the ionosphere.
Yes, we will look at the phase, but this is a bit trickier, but we can get the phase, so there's still a lot of works.
So you assume some scattering or no
Yes,
scattering?
there is work that has been done. So one of the things is that we have some source in the sky, and since the ionosphere is moving, and that should be shown in the phase. So people are interested in that, but this alone is very lot of work. So yeah.
Okay, thank you. Any other question?
Is there any value in using the high band array from a low cost station for scintillation?
Yes. So that's the people. So they have been used. There are a lot of publications, but the problem currently with high band is that allows only single beam, only single beam. There is currently there is open project that investigates multi beams. There is a Dante project that is funded from EU to create new high band antennas to have more than one beam. But in my work, I need more than one beam. So
Okay.
I personally don't use it. But okay, yes. Thank you.
Just one additional question. So what would make your this work even more robust? Like, do you need more telescopes in other places of the world?
First of all, I need to prove the concept of, if I look at this map, I need to be confident that every point here is correct, every value that is measured is correct. We are not yet at that point. There is additional effects such as side offset effects very highly. So what we need multiple side of lines that we can trust that the results, and we are not here. When we are there, then we can say add more stations and add and more coverage of sky. So this is work in progress.
Okay. If there are no other questions, we can thank Janis once more. The next speaker is Puru.
Actually, sorry, do you have a newer version of this presentation? Because I think I uploaded another one.
Hello and welcome. Let's wait a moment if we can maybe get a newer version of the PDF because it has nicer pictures. Yes. Can I get a pointer or a laser thing or something?
Yeah, we have it.
Oh, excellent.
Oh, yeah.
Okay, great, thanks. So, I'm going to talk to you about Suomi 100 ASCAT ionospheric heater campaign review. We're going to take a small look at the Suomi 100 satellite and then the ASCAT heater system. Then we're going to talk about the campaign, the several flybys that were done as part of it. Then we're going to look at some antenna patterns, ionospheric or auxiliary measurements, some ray tracing simulations. Then we're going to take a very detailed low-level look at the signal as well as Suomi 100 operations and then conclude. So, Suomi 100 is a 1U research CubeSat launched in December of 2018. And one of the payloads is a radio spectrometer, the hearer, which is what we are going to be concentrating on. The other instrument is an optical camera for aurora photography, but we're not going to be talking about that today. First results from this were already reported by Kallio et al. In 2022, and they concentrated on some of the December flyby campaign reviews, and now we're going to take a look at more of those flybys. And the ASCAT high-frequency heating facility is located in Tromsø, Norway. It has a wide range of different types of antennas, as well as some supporting VHF and UHF radars. And we're going to utilize here the Array 1, which is 5.4 to 8 MHz, and then some VHF capabilities. Okay, so these are the flybys that we are concentrating on. So the campaign was conducted during the December of 2020, and we have 2 morning flybys on the December 8th and 9th, and 1 evening flyby on the evening of December 8th. And you can see the ground track of the satellite, if I can, yes, excellent. So the morning flybys start from the Arctic and then come to the pass over the Ayscot and then come over the Central Europe, and the evening flyby starts from the Central Europe and goes over to Northern Canada. So the goal here is to, well, first of all, identify the Ayscot signal using the RR radiometer, but hopefully also study the ionosphere itself by seeing how it interacts with the transmitted heater and then what we can read from that. So here are the actual HRR measurements from all of the flybys that I just showed. The black circles denote the parts that have been identified as the signal based upon satellite positioning data as derived from 2-line elements and so on. And the numbers are HRR count values, which basically show the magnitude of the electric field as let's say, as seen by the Suomi satellite. And it should be noted that the signal that is being transmitted by the Ayscot heater is of rather short duration. It's only 10 seconds or so. So all of these flybys are a lot longer, but we will take a look at this signal in detail in the timescales of seconds in just a moment. We also have antenna patterns. Now these plots show the ground track of the Suomi satellite, and then they have the Ayscot heater's signal, and this is calculated from the power data that we have received from Ayscot for each of the flybys separately, and then the Suomi SATA position has been superimposed there based upon the 2-line element orbital positioning data. Now the key takeaway here is that all the successful flybys are quite close to the high amplitude signal areas of the Ayscot heater, but they are slightly different each time. This is due to the fact that the signal was a bit different in shape in all of the flybys, and 2 different frequencies were also used. Then we have some auxiliary ionospheric data. VHF measurements were conducted on both of the morning flybys to see up to 200 kilometers. Basically, what is the state of the ionosphere with regards to signal propagation. Now, the key takeaway from the VHF measurements is that there is nothing significant in the ionosphere during the flybys, so we don't foresee any issues arising from there. There is a sporadic E layer visible in, I think, approximately here on the December 9th, but we don't see that as impairing the heater signal in any way. We also took a look at a lot of space weather indicators for the flybys, and in contrast to the earlier talks, the space weather during early December was very calm, so there is basically nothing in the auxiliary data. Now this is and also nothing on the ski inclination indexes and stuff like that, which is a good and a bad thing, because it's good that we get the clean signal and can analyze it, but I would have maybe preferred there to be some ski dilation, so we could claim that the HRR has identified some ski dilation. We also did ray tracing simulations on the signal propagation. These were done using the, I think it's Aalto-Ray, the program, and then we input some IRI model values there to get the state of the ionosphere. And key takeaway here is that the signal propagates really well in the vicinity of the Ayscot heater. So again, there should be no issues with receiving the signal on Suomi SATA. And then we come to the more detailed part about the signals. So here we again have the count values now in red, and we have superimposed on them simulated electric field values as should be experienced by Suomi-Sata during the flybys. They are these kind of blocky plots because the approximately 10 seconds long signal is segmented in these kind of ramps. You can also see that there are two different kinds of ramps being used here, depending on the signal type. And also the time scales are now only 20 seconds or so for each of the flybys. And now comes the interesting part, because we are now in the very low time, very high time resolution and studying these things. You notice that there are these white gaps in the HRR measurements. These are due to Suomi-Sata satellites' beacon operations. So in the previous plots where we had these continuous values of the count data, it was not actually seconds on the x-axis, it was like the back-to-back plot of all the measurements. So in reality, the Suomi-Sata satellite's beacon transmits during the measurements approximately every 4 seconds or so, basic housekeeping data and stuff like that. So it does make it a bit more difficult to exactly pinpoint this signal shape onto what is being measured here. So, and in addition to the beacon operation, there are several different types of intrinsic delays on the system related to file input-output and microcontroller operations and so on. So this kind of very detailed fitting of the signal, the simulated electric field to the HRR count values is actually quite a lot of work. And I would have hoped to give you conclusive evidence based upon all of this, but unfortunately we are still somewhat in the middle of analysis, and we hope to submit this paper soon, so we're gonna have to just jump to conclusions. So we've done 3 successful flybys and identified the HRR signal from the data. We have compared the simulated signal and the HRR output in very minute detail level. We have studied quite extensively the state of the ionosphere affecting the studies, and especially the signal propagation part, and analysis is ongoing. This was done in December 2020, the flyby. We have also used the same method with a different ionospheric heater, the HARP, and another paper is coming up on that analysis. And Suomi-Sata and HRR are still operational even 8 years after launch. So we are planning more of this type of ionospheric heater campaigns, and hopefully we can make quite a lot of them as well. And as a final note, if you want to know more about the further adventures of Suomi-Sata, please come to tomorrow's talk by Esa Kallio, who is also my boss, at 13:45 at Palaver. Thank you.
Any questions for our speaker?
Maybe just a comment from IceCat. Thanks for showing your data. And the IceCat heater at the moment is not very healthy, and we are trying to get the group together to work together towards a new heating facility. So maybe you want to join that to ensure we have heating measurements also in the future. I can talk to you extra about it.
That would be nice to have this capability also in the future.
Okay, any other questions or comments? I had a very naive question about these ray tracing simulations that you do, or anyone in this ionosphere community does. Is it usually assumed like isotropic scattering, or like are there like large scale gradients considered in these days? Or what kind of propagation model for photons do you?
I I haven't actually done the simulator myself, so I can't comment from the top of my head. I believe these are based upon the already. Are you, by chance, the author of the paper and the actual simulator?
I'm not the simulator, but
I can bring them.
Yes, hey. So I'm working with the RY. So the propagation is based on the Hamiltonian calculations of Platon Hartree and Booker-Patrick.
Okay, thanks. Okay, thank you. So you conserve frequency, but it's like some small angle scattering. Yes, I see.
It considers the electron density background from IRI and then also the collision frequencies.
No, I was just curious, like, is it isotropically or anisotropically? Because the density can vary in delta n or n.
Yeah, in these plots there is the three-dimensional structure.
Interesting. Thank you. Well, we can thank our speaker one more time. If there are no other questions. Our next talk is by Marcus Pedersen.
Hello everyone. I'm Marcus Pedersen. I'm a postdoc at the University of Oslo. And I'll be talking a little bit today about our recent project with the European Space Agency. And some of our results are about calculating Joule heating and neutral density enhancements during geomagnetic storms. And this is the title of my talk today. So I'll start off with give some essential background information that I think is good to know. And then I'm going to separate the main parts of the talk into two parts. So first I'll explain what we see in the Joule heating that takes place, and then the following neutral density enhancements that happens during the geomagnetic storms. And then I'm going to finish off with a summary and a conclusion. So just to say, like, okay, the two main channels that the upper atmosphere gets energy from the sun is either through the EUV radiation, which happens on the daylit side of Earth, and this can be fairly predictable because, okay, it follows the solar cycle, and it can increase the neutral densities by a factor of 10 between the solar minimum and the solar maximum. But it's not, I mean, it's fairly predictable. And the second source that the upper atmosphere gets energy from the sun is through the solar wind. So when the solar wind has, for example, turbulent structures like CMEs and high-speed streams, which can strongly couple with the magnetosphere, it funnels energy down the magnetic field lines, which gets dissipated in Joule heating close to the polar regions. And this Joule heating increases the neutral densities, which adds significant amount of drag on satellites, for example. And this can be very difficult for satellite operators to predict and to do the necessary, let's say, they might need to do some maneuvers to make sure we don't get a satellite collision happening, or to know exactly where they will be at any point in the future going on throughout the geomagnetic storm. So we're trying to look at this second, the solar wind neutral density enhancements that take place. And our data source is that we have a list of geomagnetic storms. And we have this from 1996 to 2024. But in our study here, we use from 2010 to 2024. And we have separated each of the geomagnetic storm phases. So you can see here, let's see. So you see here, this is the main phase of one example storm. So we begin the storm around where the SUM-H goes below less than minus 15 nanotesla, roughly, depending on the SUM-H characteristic. And then the main phase ends at the SUM-H minimum, and then we have a recovery phase that lasts until the SUM-H has recovered to more than minus 15 nanotesla. And we do this, we have 326 geomagnetic storms since 2010 and 2024, and we separate the geomagnetic storm drivers into those that are driven by high-speed streams and those that are driven by coronal mass ejections. And if you're interested in this detection of geomagnetic storms, or GICs for that matter, we have a poster session about this later afternoon today. So, to start with the Joule heating, it's a statistical study using those geomagnetic storms. And we calculate the Joule heating, Anita mentioned it a bit earlier, using a new method developed by Heikki and Hamake. And we use data from the SuperMag prime magnetometers, the Ampere satellites, and electric field from superdown. And to briefly mention on the way we do it, we calculate the Joule heating based on the current and the electric field. And then we geometrically rewrite the expression using the amplitude of the currents and the electric field, and we have a term for the conductivity ratio that we find using empirical formulas. And we get the divergence free and the curl free from Supermag and Ampere. You can see some figures here on the top right. This is one example moment. And then we get the electric field from superdown, and then we can produce Joule heating maps in the entire northern hemisphere above 40 degrees magnetic latitude. We exclude the neutral winds, because we have no good coverage of the neutral winds throughout those geomagnetic storms. And there was now recently submitted a paper on this method and on the Joule heating part, which you can find in a preprint if you're interested at ESS Open Archives. So, the statistical study, we do a superposed epoch analysis. And we superimpose the main phase as one epoch time, and the end of the main phase as a second epoch time, and the end of the recovery phase as a third epoch time. And then we stretch and compress the duration of the main phases and recovery phases so that they align for each storm, and we represent the time as the median duration of the storms included in this superposed epoch analysis. So here you can see this is the northern hemisphere integrated Joule heating in northern hemisphere during magnetic cloud-driven storms. And we can see at the very beginning of the storm onset, there is a gradual increase in Joule heating toward the end of the main phase. And then when the main phase begins, the Joule heating typically decreases going into the main phase. And we can also look for the two other drivers. In the top are the ones driven by high-speed streams. We can see that there is a much less amount of Joule heating taking place throughout high-speed streams, and it's quite flat profile throughout the main phase. And for sheet-driven storms, you have a rapid increase at the beginning of the main phase, and that stays high until the end of the main phase, before you have a sharp decrease in Joule heating in northern hemisphere. And there is quite, the main phase duration is pretty short for sheets compared to, for example, magnetic clouds, which has a far longer duration of high Joule heating. So we have those maps of the Joule heating in the northern hemisphere. And you can see at the top is 20% into the main phase for the three different drivers. 20% into the main phase, there is strong Joule heating for sheets, as we could see. They sharply begin with this turbulent IMF structure. They have a very quick onset in Joule heating. And for the other two drivers, there's not so much going on at this time. But toward the end of the main phase, we can see that all three drivers, in particular, those that are driven by magnetic clouds, have a much longer extended magnetic local time sector and in magnetic latitude. So toward the end of the main phase is where we see the largest Joule heating in those two drivers, while sheets can have it from the very beginning onward too. So this is to look quickly at the Joule heating. Now, the Joule heating expands the atmosphere, heats it up, and we have a density enhancement that follows. So using the same geomagnetic storms, we have used data from the SWARM satellites and the GRACE satellites. And those satellites, they operate since 2010 to 2024 in this study, and they have different altitudes. So we needed to first normalize the altitude profile in some way. So what we did, we was calculating the relative change. So we're looking at percentage change in density enhancement during those storms. And this can be calculated, as you see here, with the observed density minus some quiet time density. And we decided that the quiet density can be, we put it as the 3 quietest days per satellite per storm. And this has an altitude dependence, as you can see, so it doesn't completely remove it. And that is because in hydrostatic equilibrium, one can see that, okay, there remains an altitude dependence in this expression, which we can adjust for using some exponent terms, depending on the altitude of the satellite. And in the bottom, you can see an example of this being done for one of the storms, where we have adjusted it to 450 kilometer altitude. And we do this so that we can perform statistics on the orbit average relative change during those geomagnetic storms. And we just looked at the new Joule heating for. So here is a similar superposed epoch analysis of the relative change at 450 kilometer altitude. What you can see at the very beginning, this is 12 hours before the storm begins. There's already some enhancement, around 30–40%. And that is because the quietest days are really quiet compared to even the nominal days. So the nominal day, even if we were to prolong this, let's say 1 or 2 days before, it will still hover around 30%. So the quietest day is really quiet. And at the onset of the geometric storm, we see a steady increase, which is far more smooth than what we see during the Joule hitting, as it is a prolonged effect afterward. And we can see the largest typical relative changes occurring throughout magnetic cloud-driven storms, which can be explained because it has the longest main phase interval with strong Joule hitting. And we have, for example, the sharpest increase in sheets. But also, if you look at this, so we have this time called T1/2, which is the relaxation time from the peak until it has gotten to half the pre-storm level. It is typically much longer during high-speed stream storms, which could be explained, for example, it's known that they have a lot of galvanic fluctuations and continuous reconnection in the recovery phase. So the prolonged impact of high-speed streams is typically longer than during CMEs, even though that the Joule hitting and the density enhancements can be higher during CMEs. So this is some of the, So this is just to summarize. In the top panel, this is all of the storms combined. Now we don't look at the driver. And in the top panel, you can see the Joule hitting. In the northern hemisphere, it sharply increases at the beginning of the storm main phase, and then it terminates very close to the end of the main phase. Well, we have a much more gradual response in the density enhancement. That can last a little bit into the recovery phase, and then it slowly drops off afterward. So just to conclude, we are working on 2 manuscripts. One is for the Joule hitting, which has just been submitted. If you're interested, you can find it in preprint here. And the second one will be on this neutral density part, which will come later. And, well, we have 2 new datasets. This dataset about the Joule hitting will also be published with the paper. So if anybody is interested in studying Joule hitting throughout geometric storms, it will be open. And it's the same with these altitude-adjusted relative changes for GRACE, and the swarm satellites will also be available. So we do see some differences, both in the Joule hitting and in the neutral density enhancements, depending on what is the geomagnetic storm driver, whether it's a high-speed stream or an ICME sheet or the magnetic cloud structure of the ICME. And we have the largest density changes occurring during magnetic cloud-driven storm, but this, the longest prolonged effect during those that are driven by high-speed streams. And for all of the storms, the Joule hitting rapidly decreases at the end of the main phase, while this density change is much more steady and slowly decreases throughout the recovery phase. So that summarizes. Thank you.
Thank you, Marcus. Any questions for Marcus?
Thank you. This is about the one-hammocky method, so if you don't, understandable if you don't know. So about the super radar measurements, so they tend to disappear when there is very much activity. Did you see this problem in your storm study, and how did you avoid the complications due to that problem?
Yes. Yes, I can take the microphone.
Yeah.
So yes, we did see this, definitely. Like if there's no backscatter, it just drops completely, and you get no electric field. And that does happen, and we tried to make a flag for it. So we have compared it to, let's see if we go quickly back to the Ampere data that we have, because Ampere also has full coverage. So we tried to compare, the boundary, because it comes from the Zettner boundary, and whenever this boundary quickly drops, we made a flag that we compare it to the Ampere boundary, and if it's completely in disagreement, then we flag it as not good Joule hitting, and it has not been included in this. Yeah.
If I may big add, so this Superdan, as you know, so they have this statistical model.
Yes, they do.
So actually, I think we were using not just the points where the measurements are, but the statistical model.
Yeah. Okay. Yeah.
And I think what Marcus was a lot talking about was this zero boundary, if that sounds so. That is now flat.
Yeah. So yeah, so we have this, and it's explained in the paper exactly the criteria that we use to when we eliminate.
If anyone else has any comments or questions, we still have a lot of time. Okay. If I may ask, you mentioned that because of these Alvin waves or something.
Yeah.
After high-speed stream.
Yes.
But you also like what's the relationship there between Alvin waves and
Yeah.
that?
Yeah, so it is, I think it has been shown in many previous studies, this hill current, this high intensity, long duration AE activity. And because in the high-speed stream is an open streamlines, they're more prone to Aldeni fluctuations in the solar wind. And this can make the BZ component also the northward and then southward again, making a new reconnection event, which might not be equally strong as the main storm, but it can sit along with new Joule leading coming in, new density enhancements, which can prolong the whole effect of the storm.
Do you think this is also the case with the sheet region, or?
That's a good question. I don't think as much, because the sheets are at least much shorter in the main phase duration, and then after the sheet you have this main ejecta coming like from the ICME. So I think it's high-speed streams are very prone to it, at least.
Thank you. Let's thank Marcus once again. For our final talk, by Fabrizio.
Alright, okay, so hello everyone, I'm Fabrizio and I'm going to present some advances that I have been doing over the NeQuick model. So first of all, what's NeQuick? It's an atmospheric model that's currently adopted by Galileo's system, so the GNSS system from Europe. All of our cell phones nowadays have NeQuick implemented in it to correct the atmospheric delay and improve GNSS positioning. It was developed by ICTP in Italy and it's with funds from ESA. It's also a default option in RI, already, since 2007, mainly to describe the topside ionosphere in the beginning, was also utilized for the plasmasphere, but with recent developments, RI is adopting other options for the plasmasphere. The code is open source and it's in Fortran. I have my own implementation in Python, and it's a little bit faster for global displays like this representation for the NMF2 over the atmosphere. And the outputs are basically quick computations of the electron density, HMF2, NMF2, and total electron content. So there are a few limitations in NeQuick, and that's what I'm going to explore in this presentation. One of the main limitations that I have investigated since 2018 during that paper, it's that NeQuick represents the electron dense profile by a modified abstent function. And here is an example of the abstent function, which is an exponential decay with the altitude. And they utilize a scale high here, which is basically constant. In the profile, it's not exactly constant because there are some other variables here, but these variables are all constant. So we can more or less assume that's constant. At least the result resembles a constant scale height. And this scale height to be constant is not, it works, but can be improved. And many models actually utilize this scale height constant in the ionosphere. And here, just to clarify this, I have utilized here incurrence character hardware measurements from Madrigal, and these black dots are the dots of the electron density profile, and the blue line is if you try to fit this profile with a constant scale height, and you see that doesn't match so well. So we have investigated this paper about a linear scale height, if it works better, and it seems to be working better because it bends like the red line. Of course, this is just one example, but this happens very often. It's working. Now it's working. Okay. So, and we know that this idea of using a linear scale height was mainly done in 2016 by Olivares Pulido And it has used GNSS radio occultation to check that. And in this left plot, here you can see black dots, which are observations of the scale height, and then the red line is a fit of the linear scale height. And this happens a lot in many GNSS profiles of electron nest. And there was a nice work done by Wang et al. In 2021 that has checked many ways to represent the scale height. And this work done in 2019, which represents as a linear scale height, has outperformed the other models. Like in this histogram, the more to the left, the better. So the minimum error for the fitting. So we assume that the linear scale height should be a promising thing to improve the equilibrium. Another limitation of NECWIC is that there is a non-electron density underestimation. For instance, if you look to the total electrical content measurements given by METOP and many other satellites that use COSMIC and so on, you can see like this is top side total electrical content, so from 800 kilometers to 20,000 kilometers. And we can see that throughout the year, it's basically higher, the values, the total electrical content values compared to NECWIC. This happens in many years. If you look to 2019, 2017, many solar cycles, you see similar behavior of NECWIC. So there is a room for improvement here. And one of the main limitations to make this happen is basically the linear scale height and also the plasma sphere. So let's take a look on the plasma sphere. This is a general distribution on z-axis by the x-axis. And this is the global core plasmaspheric model representation. And here we have an NECWIC representation. And you see that there is some signatures of the equatorial ionization anomaly here, going from the ionosphere to the plasmasphere. So this should be improved. And if we take a look for reference, RI+, which is another option for the plasmasphere in RI, it's a little bit more flat, the plasmasphere. So the idea is, how can we make something more close to the geomagnetic field lines? And to solve these limitations, there is a project going on here in Finland, which is named Exploring the Upper Limits of the Ionosphere, EOLIP. And the main idea is to solve these issues, but there is one large issue when we try to solve these underestimations of NECWIC. So we don't have many data on this part of the ionosphere and plasmasphere. So here we have radio occultation scale height profiles, and here we have Van Halen probes data. What do we do? We have a gap here. So how to model this gap? That's the question that we are aiming to answer. Well, some initial results of the project that we have done revision of NECWIC models. So we took the Fortran source code, we re-implemented the Fortran source code into Python, and we identified points in which we could improve both accuracy time to speed to compute things, and also this distribution of the plasmasphere and topside ionosphere. So the language is Python, the programming language is Python, the same output as NECWIC, and it takes some seconds to run a global 3D map. The formulation is very similar to NECWIC, so each of those layers of the atmosphere are represented by Epstein layers. However, we use sigma here, which is sigmoid function. I will share later for more details on the sigmoid. But the main idea of this slide is that I want to show that we are dividing the ionosphere to these layers. So there is a E region, F1 region, F2 region for the bottom side, F2 region for the top side. Then there is a large transition region here between the ionosphere and plasmasphere. And then we do have the plasmasphere. So in this equation, so most of the layers are represented by Epstein layers, like NECWIC. However, we use a sigmoid functions here, which is a way to connect the layers. So it's the transition region, basically, between the layers. And for the plasmasphere, we have adopted a linear relationship to represent the variation of the scale height, mostly. And to fit this data, we have used Van Halen's probe data. So to fit this formulation, we have used Van Halen probe's data. And then we applied some dependence of the geomagnetic latitude. So it's actually very simple modifications, just change the transition regions between the layers and also change the plasma sphere. So what happens with the results when we take a look on the NPIC implementation? So here is a distribution of geographic latitude, geomagnetic latitude by altitude. And here we have NPIC representation, and we see these signatures of the equatorial ionization anomaly up to 2,000 kilometers. That is not ideal. And then when adapt this transition region in the plasma sphere, we basically remove these these artifacts. And this is much more connected to previous representations of this specific region, if we use other options of RI. In the case of the plasma sphere, so we see the signatures of the equatorial ionization anomaly over the plasma sphere, but if we use our adaptation with Van Hallen's probe data, we can actually better represent the geomagnetic field lines structures. On numbers, how this does translate, the accuracy of the models. So we have done an evaluation using 16 years of data from total electron content given by GNSS. So we have used mainly 3 data sets like global ionospheric maps from CODE, plot tag from Swarm A, and plot tag from Cosmic satellites. NPIC has an average error of -2 to -3 TC units, so there is a general underestimation. And IonoMap, or this formulation that we have developed, also corrects not only the representations, but also this underestimation partially solves the issue. Still, there is some room for improvement here, and we are going to tackle these problems in the future. Overall, we have had an improvement of 28 to 40% on the accuracy of total electron contents. So some lessons learned from these initial results. Well, the plasma sphere of NPIC is anchored to the F2 layer. We have shown that modeling the plasma sphere as an independent layer improves NPIC, as long as you keep a transition region between these 2 layers. Well, Van Hallen's probe data can be utilized to develop plasma spheric model. This is the first model as long as it's published nowadays. This is the first model using Van Hallen's probes to describe the plasma sphere. And then there is this insight that the linear scale high is promising to improve the topside ionosphere. Currently, I have not yet utilized the linear scale high, but in the future, I'm going to improve IonoMap with this. So one point also for the future, about this paper published in JRL, is that how can we cover the data gaps? This is still something that's hard for us to answer, but we have found a way. So this is that data gaps in the plasma sphere that we don't have so much coverage of the measurements. However, we took a look on this paper over the ARAS mission, which measures wave spectra basically, and they actually can cover the data gaps that we are looking for. So there was in previous there was a gap in measurements like for this whole region here, and with ARAS mission we can actually cover this. So in the future, probably I'm going to include ARAS mission as well. So just some heads up for EGU 26 that we, together with the International Association of Geodesy, we have a special session on geodetic observation methods for space weather. And with that, I end my presentation. I would like to acknowledge my partners and everyone here. Thank you.
Thank you, Fabrizio. Any questions?
So I noticed NE could exist, but I haven't reduced it. So if you make some improvements, do you think that would also improve then IRI model, because you told that IRI is taking the topside ionosphere from NE quick?
Yes, definitely. We should improve NPIC, and then we hope that then RI will also utilize the new version of NPIC. But that's the idea, that's the whole goal, to improve RI at the end of the day. And also RI is looking for new options of the plasma sphere. So they have included in RI 2020 a few more options, but still it's undergoing all the studies to check which one is the best or if there is any other best option.
Any other questions? Okay, if not, we can thank. Oh, I can ask a question if you would like. Okay, about this wave spectra you were showing, like what kind of waves are they? Because the ionosphere is not fully ionized, so I'm assuming this is some drift waves or sort of.
The plasma sphere is fully ionized.
Oh, right. Okay.
Yeah.
Like I told you, I'm very naive. Thank you.
No, it's fine. Like these options are from the plasma sphere.
Right. Okay.
Yeah.
But what waves are these? Are
UHF.
okay. Okay. No, I mean I'm just curious because like you need to like to get the density you need to fit the dispersion
Yes,
relation.
I'm not the one that have done this conversion, but
okay.
yeah.
Okay, thank you. Okay, let's thank Fabrizio once more. And with that, we can close the session. And thank you to all the speakers. I think this is the last session of today.
Okay, so, right, so if you don't know my background, I was the Irish station of Bird, and then the Irish station of Finland, one thing you mentioned was not being able to do
No, not simultaneous, multi-beam.
Yeah, that's what I mean.
Well, eight bays, so.
So you have
Joo, pyrkimys on parantunut häiriöistä esityksen aikana. Esa-Kalle on sitten sun papereita.
It's a one option. Analog beamform, which is what we're doing. So the first thing that you can actually and then each individual tile is like an LP tile in that it has a complete array. Now, if you have a couple of sources that are roughly in the same area of the sky, then your next option is to have the wideband mode. So wide beam mode, sorry. So here what you do is you don't drop 15 out of 16. You may drop, for example, a line of sub-antennas within the tile, which is aligned with the two sources that you want to monitor. And so therefore, you've got a nice band beam that crosses those two sources. And you've got high resolution one direction, broad resolution in the other direction. And that's an adaptive subarray within the tile that you change depending on which sector of the sky you're looking at. So that's your second option. Well, I don't know because I'm not a scintillation person, but I'm just throwing out options and then you can decide whether it's going to work for you or not. Okay, so your next option is to go to mixed mode observing. So in the old days, in the old WOFAR 1.0, 1.3, they talked about these RC units, and plus use modes 3, 5, and 7. These days they've got different names. I don't know version, they call it something different. But what you can do is you can have, you build a subarray. So within your low band array, you'll have a subarray of a certain number of antennas that you're going to use. Then you'll have a separate high band subarray, and that high band subarray will be, you don't need as many. The ratio is about 1:16 if you want to have roughly hours because there's 16 sub-elements in a tile compared to 1. So Kyra, what we did is we were doing scintillation against two sources, which was Casse and Sige. So what we did, and this is modes 3 and 5, so the low band array has got 40 antennas, because Kyra is a smaller station, so it's only got 40 antennas. So we had 40 low band antennas, which were doing basically all sky and anything we want. Then we had the first subarray, which was 3 high-band antennas looking at Cygnus A. The second high-band subarray, which was 3 antennas looking at Cas A. And that way you could get simultaneous Cas A and Sig A, as well as getting all sky and low band. So that's your next option. Now, if you have a bigger station, like the UK 608 station, you'll have these full So then what you want to do is you want to do it so you're taking, I think if I remember rightly, there's 84 low bands that you want to use, and then you have 2 subarrays of 6 tiles each. And those 6 tiles, you form them as Manx arrays because that is optimal to get the best possible beam that you want. And so you've got 2 Manx arrays looking at Sig A and Cas A, and then you've got the rest of the LBA. And because of this ratio of the number of elements inside tile compared to the number of, so you've got basically 6 to 1. That's how you're going to split your arrays between high band and low band. But it depends on your source. So obviously if you've got a steep spectrum source, you're going to want to tune this accordingly. So you may want to change that balance according to what you want to do. But for the experiments that we were doing as demonstrators, 16 to 1 is fine. So then your next option, sorry I'm throwing millions of options at you at the moment, is you can do a time decimation. So here what you're doing is you're splitting the array, you're grabbing lots and lots of data in real time, but you're chopping it in real time as well. So that allows you to, what we were doing is we were actually doing multi-frequency correlation. So we were looking basically everywhere at once, but at 10 separate frequencies. And then we could split it and do various other things. But you can do the same thing in a beam sense. So rather than having 10 frequencies on the sky, you can have 10 beams on the sky. And again, you're just doing it as a time decimation option. But again, I mean, you've got a balance here. All of these are a balance because you don't have the ability to run both rays simultaneously. But just saying, I know this is not what you meant, but just saying blanketly that you cannot do multi-beam with the HPA, well, it depends. So, and this is why I got a bit.
Well, so if you drop antennas, you lose sensitivity.
Yeah, sure. The Cas A is strong, and Sig A is strong.
I have not explored that often, so yeah, that's an interesting thing to think about. So I know that there is a project update HBA antennas, so so that would be that you use multi-beam, but you don't lose sensitivity. So
that's the long term goal.
That's a great.
Sure.
But the problem here is that is not I think in the standard software. That's something that you need to dig up how to actually do it. So it's not that well documented.
So the stuff, all the things that I've just talked about now, all of this stuff is fairly well documented. It's just using standard software.
Oh, okay. Yeah.
So, and it's all handled at the script level, so you do not have to hack either the RSP, I can't remember what it's called, not RSP CTL, but it's the daemon that RSP CTL is talking to, nor do you have to hack anything within the SPU or it's in the RCU controllers. Because within the low-pass station, within the sub-rack assemblies, you've got these 96 or 192 of these RCUs. You don't have to hack any of that software. Everything is handled at a script level, at the LCU level, just using the standard Astron RCU CTL commands and the SW level commands. You don't have to go down and hack it.
Okay, yeah.
No hacking involved.
So just first opinion, maybe time shifting or time chopping could be interesting to try. It's not losing sensitivity, but you just switching.
Yeah. Okay. Right. So on that, so for the hiring experiment, what we did is we ended up creating what we call a medium speed product. So if you just use the standard subband statistics and beamlet statistics out of that Astron provides, you're getting a 1 second cadence, and that's not fast enough for simulation. On the other hand, you don't want to take the 195 kilohertz raw data because then you're going to fill the disks up super quickly. So what we were doing is we had like an intermediate mode where we were basically taking the data, we were turning it into Stokes parameters immediately, and then we were integrating over a shorter, a variable cadence that we could determine, and we were using approximately 100 hertz. So that was roughly what we thought was suitable for some of the ice skate experiments that we're doing currently. Now, you may decide that that's too fast, or you can slow it down, or whatever. But then that's another thing that you could explore. You can explore time dependency. But again, it depends how many sources are you trying to get. What is the strength of those sources as a function of spectrum? Do you really want to get them all simultaneously, or can you afford to time chop? And if your time chopping is once per second enough, or do you want to do it once every 100th of a second or 10th of a second? I don't know. And then there's all the subarray options, where you're basically splitting the arrays by having your tiles doing sources with, like, Manx subarrays, and then having the LBA doing the stuff, doing its thing as well. Anyway, there you go. There's a whole pile of ideas to go about.
Actually, I maybe told myself what is called the Zurkov. They actually connected to Graph.
Right. Okay.
Okay.
So
physically, the whole just online.
Yeah. Oh, okay. Right. Okay. So now, yes. Right. Now I know who you are. Yes. Okay. Yes. Right. Yes. Okay. Because I used to be, up until about a month ago, the craft representative for Finland. So Finland, well, I was representing Suomen Akatemia, which is the Finnish Research Council. They've now pulled out. So at the moment, Finland doesn't have a representative.
So you draw.
So I'm not doing it now, but until we find out who's going to do it next, that's next. Now, you guys are all from Urbana, right? Right, okay, so I need to talk to you guys anyway for a totally separate thing. Which has got nothing to do with craft, and it's got nothing to do with low power scintillation. It's actually to do with laser monitoring. And this is to do with the Urbana interferometer and the ability of maybe us trying to get some sort of maser VLBI thing going.
We are most, so I personally, so there is a local signal station meeting, so you probably attend, so this is where we connect in Zoom.
Yeah.
So I'm the person that attends those meetings. So, so we are doing measure monitoring, we are also doing with multiple telescopes. So this is something that we are interested in discussing, but we are also interested in discussing what is currently going in the Chiron discussion that are currently responsible for the operations. So we have some ongoing projects about space weather, and one of the discussions that we would like to ask is we would like to touch with person that we would like to do some kind of collaboration observation with Chiron.
That's me.
That's right. So we earlier today we had talking with Leo Sokin, and he was not sure who is actually the best person to talk, that we understood. So that is one discussion. So we have the